Welcome to another coding session where I'm creating a new programming language from scratch. Last week we introduced types, so now you can, for example, define a bool like this. This means it's an enum type with which is either true or false. Types can have type variables, which are lowercase, and they can also be recursive. So, for example, this is the definition of a linked list. So if you have list int, for example, this is either empty, which means the list is empty, or more, which means it's not empty, and then it will contain an int and basically the rest of the list. Yeah, these recursive types, they don't quite work in all cases right now. So when we run this file, then you see that there is this make list function down here. Basically, you tell it the length of the list, and then it just creates a list that contains, let's say, 0, that only contains zeros with the given length. So it checks is the length 0, and this means that it switches on that. If it is 0, or if the length should be 0, then it's just an empty list. If it's more, then it creates this more symbol containing a 0, and basically the rest of the list is a recursive call to make list with the length -1. Right, this kind of works. So if you call make list of 5, for example, you will get some out of 3, let's say. You get more of empty. So you get a list with 3 elements. Yeah, but the type checking is not working out in every case. So here's the code of the function basically analyzed and type checked. And we can see that this is a function that takes an int, which is this argument here. And yeah, we create a 0, then we call the equals function, equals of int and 0 with our argument and the newly created 0. Then we switch on that and we're like, okay, if the length is 0, then we just create an empty symbol. If it's not 0, then we call ourselves recursively. And you can see that the results of those switch branches, they are basically empty in this one case, and they are this in the other case. So this is a more tag containing an int, and yeah, the formatting is kind of messed up. There should be parentheses around this, but basically a recursive list. So either empty or more containing an int and another recursive list. And this right here means if you want to inspect this type further, just look at the type that is like one layer outside of this. So inside of this more tag, it will actually contain another like enum that's either empty or more. And then when we have this right here, which is empty, and we have this, which is more of int and other stuff, they get joined to something that is this. It's either empty from here, or it's more containing an int from down here, and this. And this is correct, but it's like not the minimal way to represent the type. So for example, you can see that we could just write this highlighted thing and it would mean the same thing. Because outside of that, there's an enum that is either empty or more containing an int. And then inside of that is empty or more containing an int, which is then recursive. But we could just as easily remove this part. Right, so yeah, that's what we're going to do. Basically, we need to ask ourselves, what does it even mean for two types to be the same type or to be assignable to another when we have recursive types? Yeah, let me switch to my iPad and draw some things. Because currently the type algorithms that we use, they're kind of written ad hoc, you know. There are these down here, yeah. So you can, for example, join two types. Yeah, and we implemented some of that, but obviously this is not correct if we have recursive types. Or let's say that we want to check if two types are equal. We do that somewhere. Yeah, up here. And this is not quite correct because there can be multiple representations of basically the same type, like what we saw just here. So yeah, let's change that. Yeah, basically our types are trees right now. We have a yogurt type, which is a tree structure that tells us which kind of type it is. So for example, for the enum from before, this is kind of like this. We have an enum with two variants, like two children, empty and more. The empty variant contains nothing. The more variant contains an int and, you know, like a recursive type to up here. And now we want to ask, like, do some type operations. We want to be able, for example, if we have a switch, we want to be able to navigate into types. We want to check if two types are equal. We want to check if one type is assignable to another type, and so on. And, you know, thinking about all of these operations on concrete types is kind of difficult. So yeah, for the rest of this explanation, I'm just going to simplify types into, you know, something like this. For example, we have a type A that maybe contains a B, and C, which contains D and E. Oh, maybe not E, maybe it just recurses up here. So this is, you know, types aren't actually trees because, you know, they can, like, we have cycles here. Yeah. Okay, so the first operation on types that we want to do is be able to navigate down into a type. And you can think of this like we have a type A, which is, I don't know, an enum maybe, and we switch on that and we want to know what is the type of this one enum variant. And we can't just say, you know, we take that subtree, C containing D containing a recursive type to somewhere. Yeah, we can't say that because, well, this type right here doesn't even, like, it doesn't point inside the type. If you remember, like in the data structure, and the type data structure, this is our tree. It basically just says, well, go this many levels up the tree. And that doesn't work. Like, if you navigate into that, we need to adjust these recursive types. And I think what we can do is just we check which types reference the root type. That basically doesn't, this root type won't exist if we navigate down into a type. And then we replace each of these recursive types with a type that looks like the root type, except the part that we are navigating into is replaced with a recursive type, like this. So that's like the first step. If we want to navigate into a type, we do that, but these recursive types which reference the root, they kind of wrap around. So as we navigate into a type, we extend the type at the bottom so that we never actually reach a recursive type, or like the, you know, the marker that this type is recursive. Next, joining types. Let's say we have a type A, which either contains itself. No, let's do it like this. It either contains itself or it contains B. And then we have another type that also either contains itself or it contains B. Or it contains C. Yeah. Like if we were to navigate down here, for example, that would basically result in this type. Type B. Oh, wait. Yeah, sorry. These should also be recursive. Like this. Kind of convoluted maybe, but well. A type B, which contains an A, which then either contains a recursive type A, or it contains a B, which then again contains A. Yeah, so if you follow the red thing, you get that down there. And maybe let's also do that for the other type. So if we navigate to this C type, really we are getting this type. Yeah. And with that in mind, how can we join these types? I'm gonna represent joining as like the in mathematics for sets, there's also this join operator, this union operator. So how can we join types? Basically, we want to, let's just think about this logically. The root will be A, because each of these types has A as root. And then there are three children, A, B, and C. So there is some A, B, and C. And they are also some kind of type. And actually the A type is recursive in both cases. So I think the A type should actually be this. Yeah. And then there's B and C, and here we just navigate down into these types and basically copy these types. So kind of like this. B, and then we have the C type, which is this. Let's just move that there. Why not? Yeah, so that's the idea for joining types. Just check, is the root node the same? And then, join. Okay, this on the left is kind of fishy. Like, maybe let's think a bit clearer about how to do that. So if we ever find ourselves with an enum type where one variant is only exists in one of the join types, then we can just we can just navigate down there and take that type as it is and plop that in there. But basically for this type right here, I think we need to navigate into, we need to follow these. We need to basically go down here and go down here and then join those types. Yeah, that makes sense. which basically means that we end up with the same problem. I see. Okay. So we'll have something like this. The result of joining these is this, where the B variant only occurs in this type. So it's like immediately pasted into here. Same with the C variant. But for the A variant, this is contained in both types. So in both types, we need to navigate into that and then join those again. And I think we'll just keep a track of all the types we either have joined or are currently joining. And then we're like, okay, up here, this is the, this is the result of, this is the result of joining these two types. And then when we try to recursively join those same types again, we can just replace that with a recursive type, with a recursive pointer to that type. Yeah. I think it will be clearer in code, hopefully. Okay. Joining types, checking if two types are equal is the next operation. And it's kind of similar, actually. Yeah, we just do the same thing. Checking two types are equal means we need to check that they have the same children, and then for each of these children we check if they are equal. And if they are not, like, we need to handle recursive cases. For example, if we check that, I don't know, we have the type A, which contains B, which contains A again. Like, B contains A again. And we have a type A, which contains B, which contains A, which contains B, which contains A again. If we want to check, are these types equal? The question, basically boils down to comparing the root nodes, like A and A. They are they have the same name. Sorry. So then we navigate down into that, and the children also need to be the same. So we navigate down, and we see, okay, in order to answer that question, we need to answer the question, are these types the same? The type B, A, containing being recursive, and the type B containing A, containing B, containing A, being recursive. Are these types the same? And then we check, okay, both have the same name B, and then we navigate down into them, like here. And we need to check, are those types the same? And then, basically we end up with recursively checking this. So here we need to remember what are we currently recursively checking. And if at some point we end up with that same thing, then we can just say, well, yeah, they are the same. Because up here we check if, basically when checking types, we check if they can be treated the same. Like if I have an instance of this type and of this other type, do they both support the same operations? So if I go into this field, into this enum, I switch on this, is it the same in both types? And if if we have these types, which are like, they describe the same set of values actually, and then at some point we're like, okay, that works if they are the same, then we have basically proven that in all the intermediate steps we can treat them the same. So yeah, this always works. And maybe let's talk a bit about why do we even why is checking if two types are equal? Why is that so difficult? Or like unioning types? And the reason is that types are not perfect abstraction. Like really we have our abstract universe of values like true and false and 5 and bar and I don't know what. And what types do is they draw a line around some of these values, like this, which is a mathematical set. Or like for bools, it would be this. And the problem is basically that there can be multiple ways of naming these sets. So even though they represent the same set, there are different different representations for that when you want to describe that set as a type, as a tree structure. Okay, yeah, let's just implement these and then hopefully things get more clear. Okay, yeah, I think we'll do quite a bit of type operations, and they're kind of noisy, and they don't they're not really part of the core compiling thing. So let's just create a new file, I guess. Type algorithms, type algos. Yeah, let's include that in here. Cool. And then let's just copy the join function to here. I don't know, something else. No, this is all converting stuff to yogurt. That makes sense. That makes sense to be in this file. Yeah, this right here. Checking if one type is assignable to another. That is, or specializing a type with another. Yeah. Yeah, I'm not sure about equality. Like, do we have like a map somewhere where the left side is? We have a map from yogurt signature. Oh, no, but that's just a string. Yeah, okay. I think we can just keep that like this. Yeah, let's try to remove this. Wait, first let me check if there's no, there is not. Yeah, let's remove that. And just going to check if it still compiles, and it does not. Oh, okay, so we are mapping some arguments somewhere. Get 72. Ah, right. So we have the arguments. We check are they assignable to each other? And then they need to be the same. Okay, but this is not. This, for example, should not be like should be the semantic equality of types. So I think it makes sense to not, I'm going to paste it in here so the code is not lost, but yeah, basically we want to replace this with like semantic equality types. Okay. So, yeah, what was the first operation? The operation was navigating into a type. Let's do that. Let's just define that down here, maybe. It takes a type and a name, I guess, of the member that we want to navigate into. And that returns us another yogurt type. Yeah, for yeah, this doesn't work. This doesn't work, this doesn't work, this doesn't work. Okay, let's just... And also recursive doesn't work. So the only case that can work is for enums currently. I think later we'll also add structs, something like that. Yeah, let's just say you can only navigate through enums. Cool. Dot child, dot member, dot variant. Type of variant. Oh, I like that. So you have some type. It's an enum type, and then you can say dot type of variant true, and it gives you the type of the variant true. Although it should be types, like args. Yeah, something like this. Yeah, you know what, let's just unwrap that. Yeah. And now we want to get the correct type from the variant. So variance dot get name. This should probably be like a list of types or something. Yeah. Now we want to map them. So this is basically replacing recursive types that pointed to the root node with this custom type. Like, I don't know, modified root maybe. And that's the type. It's like the type without type when all variants are the same, except the variant pointing that we navigate into. Yeah, actually that's not a to-do, that's like documentation of what this is. And maybe like adding comments is a nice thing anyway. So when navigating into the type, nicely Yeah, let's say we have our list type. List t equals empty, or more with a t and a list of t. Which really is just, here I am again, yeah. The surrounding type, yeah. Yeah, what does 1 even mean if there's no type? Yeah, like this. Okay, cool. We have an explanation. That's cool. As of variant, so we have a yogurt type. Cool. Yeah, that has to be an enum. Basically the enum that we navigate into has been replaced with a recursive type. So let's create a yogurt type. Enum. Variant, I guess it's just map from string to, sorry, string to yogurt type. This is a yogurt type. Probably this. Yeah. And then for variant in we say extension variants dot put. Yeah, and if the variant name equals the name that we're navigating into, then this will just be See. It depends on, like, we can have a type where one branch recurses with a pretty tight recursion loop, and another type is really deep and then has a recursive type. So we can't even we can't just naively decide on a recursion level, like right here. Yeah, let's just then do else variant dot. Oh, and these are map entries, so it's key and value. Yeah. Okay. Yeah, this is like something. The question is just what? I guess let's just yeah, let's fill that out later. So now we want to check the arguments, like collect the arguments, which in the end will just be a slice. And then for all of the actual variants, we just no. Yeah, for the arguments of this variant, yeah, in this case, for example, an int and the recursive type, we would then do arg args dot push arg replace recursive type with level with level 0, 1. Yeah, if there's a recursive type with, basically this right here, then this will be replaced with that newly created extension, because then this pointed to the root node. Yeah. It's type and a level. And it just switches on the type if it's recursive. If the actual level equals the level, yeah, otherwise we just return the type single. Yeah, and now the question is with what do we replace these recursive types, which point to the root node? Oh, hang on, we also need to handle the other types, because we need to call this function recursively. Well. Okay, so if it's an int, then this is just this. If it's a string, it's just this. If it's a type, then it's this. If it's never, it's yogurt. type never. If it's an enum, this is interesting. Then we basically need to map the variants. And yeah, kind of like this. And here we can replace recursive type with level +1. Nice. Yep. Okay, so if we have something like, a very deep type hierarchy, let's say the empty contains another enum, which is foo or bar, and then the bar contains a type like this. Please go 2 types up to this list. Then we want to replace that 2 with list of t as well. So when we ask what's the type of the empty variant, well, that's an enum type containing foo or bar, or recursive type of list. Yeah, actually, let's create a simpler example for some definition of simpler. Yes, like A or B. I want to create an example where we actually have like nested recursive types. B, which is then again either C or D containing this. Yes. If you switch on foo, in the case for B, the types of the arguments should not be should not have the type. C or D. If there are no good types. Should have this type, and just say what we want. That's much easier. And we can also remove some of this. If you switch on this available of this type, the argument, the enum payload, in the case for B, should have this type. That's actually readable. D containing enum A or B containing this. As you see, I'll just take the type of the variant, because it may refer to the type to the auto type that we unwrap. Having this in a type where there are no two types surrounding it is bad. So you need to wrap around. As you navigate into types, recursive types should be extended at the bottom so that you never actually reach a recursive. Yeah, that's a better explanation, I think. Regular, we need to replace all recursive types that refer to the former root type with a with an extension maybe that adds one layer. Nah. Need to extend all of it. Yeah, like this. Yeah, perfect. The original, that is the original enum, except the variant that we navigate into. This variant has been replaced with a recursive type. Beautiful. Okay, so then in here we map those. Yeah, and basically, if we have, like in this case, here's a recursive type of 2 at a depth of 2. So this refers to the root type. So that should be replaced. But if this was like this, for example, so this is the original type. If this was like this, just always recursing over this enum, that would be no problem. We could just navigate into B and take that type. So yeah, in here we just, this is the current level of this type inside of, like, counted from the root type. We start with a level of 1, and then for each level that we dig down into types, we actually increase that level by 1. And then for recursive types, only if the actual level is the same as the level, aka only if it points all the way up to the original root of the type, then we want to replace that. And maybe extend is better. Extend recursive type with level. Extend recursive types. Yeah, let's do it like this. And it takes a level, and it takes extension, which is again the other type. Okay, nice. Yeah, that seems more reasonable. And the extension is whatever we crafted up there. And because we don't know the level here, I think it makes sense to just say give a type dot recursive -1 or something, just as like a marker. And then in here we can say this will be the extension recursive level, and we replace the -1 with, you know, the actual level that we want to have. Oh man, another function. So we have a yogurt type. We have from to, and it returns a yogurt type. By the way, this does that as well. Okay, and what do we do in here? We just switch on that type. The same new variants put place recursive level from to. Obviously not, doesn't fit on one line. Well, yeah. The actual level is from, then this will just be recursive to. We can also that this, look at how readable this actually becomes. Okay, beautiful. Yeah, and here I'm just gonna say recursive, sorry, yogurt type recursive with the actual level, just because it's similar to what we do up here. Create a new yogurt type. Okay, so yeah, what do we do? Yeah, to do that, we first create an extension that root recursive types will be extended with. In this extension, and that is, you know, A or B. The -1 is just a marker. That means replace this so that it links to the new root. Beautiful. The original type recursively and replace all recursive types that reference the root with this extension, the level that we are currently at. Beautiful. Okay, yeah, I think that makes sense. We can hopefully navigate into types. That was the first algorithm, navigating into types. Yeah, the second one. Second one is joining types. What do we do here? So we have this nice section header down here. We have a header for joining types. When joining types, we need to make sure they line up. We can just join int and refer. We also need to. We also may need to extend enums. Maybe whenever you have multiple branches that evaluate two different types, when multiple branches evaluate two different types, those need to be joined to get the overall result. Yeah. In that case, we need to make sure that all types line up. You can't have one value to int and another one to string. Yeah, this process of joining types is implemented here. A more complex example. And then we'll basically, I'll write down the example that we had before. So we have an enum. First type. What's this? Enum with A or B. Joined. Yeah, it's either A or it's B containing an enum that is then either A or B, or it's a C with an enum that is either A or C. Yeah, the ifs. To enum types that are joined. The resulting is a recursive A variant as soon as either A or M, B or C, return, we know from which original type this value stems. So we have a more precise type for the contained payload. Okay. So then the question is, how do we join types? We keep a list of types. Well, yeah, let's maybe first do that and then write about how to do that. I'm gonna take a quick break. Okay, so what do we want to do? Basically, we need to, I think this needs to like accept a list of the ongoing joining that we are currently doing, so that we can then insert recursive calls into these. And like maybe before we do that, let's just look at the variants. So we have these common variants, then we have the A variants and B variants. And I think in here, we don't want this. We don't want to put in just the variant value, but instead we want to lower that. We want to check that, you know, like what we just defined up here, args of variant. Yeah, we don't just take the variants naively, but instead we say a variance is you know, a dot args of, oh, let's see, yeah, maybe like this, a variance, yeah, sure. We have the common variance, and then for each of the variants and a variance, we say we get that key, and instead of getting the value, we say args of variant. Ooh, does it? I think we can simplify this even further. We can say, like the API of that, instead of saying give me the arguments of this variant, we say extend the recursive types of this one level. Yeah, extend one level. That's nice. That is super nice. Yogurt type, and that's it. It just takes the yogurt type, returns the yogurt type. And then the variants will yeah, this should handle all different types. Like this. Yeah, if it's an int, we do this. If it's a string type, never. If it's an enum, then we want to do this right here. Yeah. We have the variant, right? We build an extension, and then we lower the variance. So here you can just do for variant in variance dot, sorry. Variant in variance do new variance, maybe. and this will be mapped from string to slice of yogurt type. Yes, and then we have the for each variant we create arguments, we push those, we map those arguments, and then we add them to the variants. So variant.name links to slice. And instead of this, we just do variant.value. Right. So this should match in. Yeah, recursive types should be unreachable. In this case, because you can't extend them, they should have been extended before. Perfect. Right, so we don't need to do this anymore. Great. And let's add this when navigating into types. To surrounding types by recursive types. That's good. Calculate self-contained types. Yeah. If you switch on the value of this type, the enum payload in case in the B case should have this type. Yeah. Can't just naively take type of the B variant. Well, it refers to the outer type that we removed. So types need to wrap around. As you navigate into types, recursive types should be extended at the bottom. Yeah. We need to extend all. Yeah, perfect. This function extends recursive calls that reference the root. So that you can take, so that you can, yeah, so that when you navigate into this type, the resulting types are still self-contained. Perfect. Yeah. Recursive type replace that. Okay, sure. Yeah, so now in here we can say we have an enum with a variance. Yeah, that makes sense. Okay. Oh, this is elegant. We can just say a equals a dot extend one level when same with b, and then this code works. Because then when we call ourselves recursively, well, nice. Okay, yeah. When we call ourselves recursively, we will always extend the type at the bottom. Yeah, so it will be a problem that we do this every time because things won't terminate. Let's just check that out and see what happens. 994. Yeah, let's I mean, this is true, but let's just add that for now and then remove that later on. Name is not in scope. Oh. True, I guess. So here the extension is, oh, it's a different extension for each variant. Yeah. So variants, we create new variants, and then, yeah, okay, and in here we create the extension like this, where the, well, this is already called variant. Extension variant if extension variant of P is variant of T. Mm-hmm. Oh. Mm-hmm. That is true. What do we do in that case? Like, I think we have like a separate thing for each type, right? Okay. So the question is what happens, or like this right here, or like for B has two types. It has the C type and it has this. Yeah, the enum should not have a single type. It can have multiple types. And inside of those types, extension, is that like a different extension for each argument? No, it's the same. I'm not, this is difficult. I'm not sure how this is supposed to work. Yeah, basically we like in this case, for example, we take the arguments. This should result in like navigating into B, switching on that should result in two types. One of them is this enum, the other one is int. And inside of this enum, B should be replaced with that. Yeah. Okay, true. So oh yeah, but we still build our original type. If B took two things, two types, int and an enum type. Yeah, now this should have two types, right? And for this type, it should be something. Mm-hmm. Replaced with a recursive type. Yeah, this, like whatever goes here should be a list. Yeah. Okay, let's do a type where both of them are recursive. In this case, you know, C should be basically a B containing what? And this perhaps, right? Oh, yeah. Hmm. Yeah, let's just say all other types stay the same. I'm not sure if this is correct, but what are we doing? Okay, so we have an enum. Sure. And for each of the variants, we want to map that into a new type. That's what we do down here. Okay. Sure. Down. New variants to put, yeah, down here. With the variant name and an enum. Okay, and a map. Yeah, that makes sense, but let's inline that in here. Like I'm just refactoring stuff to make things hopefully a little bit clearer. Okay, so an enum type definitely maps to an enum type. Correct. What is inside of that enum type? Well, here we have the variant, which is a map from string to slice. And then for each variant, we just add that to this map. Yeah, and then in the end, we result in the new variants. Cool. And with this, yeah. So for each variant, we put something into the new variants. What do we put in there? Okay, we have an enum, we're inside one variant, and there are different arguments. Now we basically want to replace one argument do we want to replace them independently? I think so. I think so, yeah. Yeah. Okay, maybe the method of like extending that type is not the most clear way to do that. And then we create the arguments. We want to extend them one layer at the bottom. How does that work for multiple? Yeah, if I want to switch on this, basically have to do 2 times. So in this type, yeah, okay. Yeah, I think all other types remain the exact same, which makes sense. Okay, let's just implement stuff. So the question is, we create arguments like this, and then we want to push an argument. And how we do that is basically this. We push arguments. So we create an extension and for all of the other arguments, which are not this one, so basically for arg_variant.value dot enumerate, I guess. The extension basically just looks at, is that arg extension variant for extension in args. Something. Here's args. Let's go with extension. And replace these with something shorter, maybe. So the extension variants, we build them up by going over the variants again. Then inside of each variant, we just put, if this is the key that we're, like if this is not the key, then we just take the value. Otherwise, if it's the key, then we map the arguments. Yeah, by just mapping over the variants or extension. Yeah, basically doesn't matter what we do here. Going over these, and then extension args.push. Yeah, if arg.index equals index, then this. Otherwise, just arg.id. I hope this works. I really hope it does. Okay, name is not a field on map field because it's the key. There, oh right, these are lists. Yeah, that's true. Oh hell yeah. this maybe. Nope. Okay, what does it say? Oh, to nothing. Right. Map string to yogurt slice. All right, we're missing the key. Yep. Yep. Let's just try this. Let's call it extend recursive types. Arg.item. Extend recursive variable value. No. Yeah, we need to map those. Well, so args is an empty list of yogurt types, and then we equate over the variable values, and we push that. And yogurt type dot, no, just args dot to slice. And this is really arg dot extend. Okay, so what's now? There's, oh, with the extension, true. Okay, okay. Replace recursive level. Slice. Well, same thing again. Okay, where is this hashed? Oh, we do have a map from yogurt type to something. Types. Yeah, okay. So maybe do that. Okay. Oh, now there should be, yeah, joining false and true. Joining true or false and false. Joining empty and more, and let's maybe fix the printing of types as like first thing to make debugging much easier. Yogurt type and enum will just be, we'll print an opening brace and closing one, and then the or thing in here, like this. Okay, yeah, so this is an enum containing true or false. This is an enum containing empty or other stuff. If okay, true or false, this is empty, this is an enum with one variant, more of int, which then contains another enum. Okay, perfect. Perfect. Sure. So then joining these types. Nice. Okay. Next, checking if types are assignable. I think there is assignable to, yeah. Oh, in the type algorithm. Okay, it's an egg type. That's like easy. So let's instead is assignable to with the yogurt types. So from yogurt type to yogurt type. Basically, what we want to check here is that when we join from and to, that then this remains the to type. What did we call the? Oh, we don't check if two types are the same right now. Okay, and let's use that. For example, when we compile a function, let's check that the function returns what it claims that it returns. Okay, so we have a function with parameters. Oh yeah, this is just yogurt body. Yeah, when we convert an egg, fun. We put this in here, we compile the body, and then we basically want to check that this returns the correct thing. So we take the return value how do we convert? I think when we convert a call, when we compile a call, then yeah, we figure out the return type like this. Yeah. So now when we compile a function, we basically want to ensure that this function has the return type. Check that matches what the function claims it is. Basically, I want our in our code right here, we just trust functions that they return the correct thing. So we don't actually like try to check if this is the same type as whatever the function claims it returns, which means that our like sophisticated joining and checking if types are equal and stuff like that, it doesn't actually get used right now. Like the simple joining, sure, that gets used, but nothing fancy. So yeah, range return type is fun.return type, and this is not the like this is an egg fun. Oh yeah, let's maybe not do this, but let's say, or let's call this egg fun, is this. Okay, let's call it fun. Egg fun. Yeah, and then we say let's take the egg fun and return that with these params. Result env. Oh, that's from here, and that's map. And that gets built because, and in which way does it get built? Basically in here we check that they are assignable to this thing. Yeah, I think we need to, it's cleaner if we do that in here as well. So here we have is assignable to, with a yogurt type and an egg type. And let's maybe add is assignable to with a slice of yogurt types to a slice of egg types. And that's basically what this does. We try to build a coherent environment, and then for each of the yogurt types, so yogurt.iter and egg.iter, we say the arg environment, sure, is A is assignable to B, or if that doesn't work, then we break it. And then for each entry in the argument environments, we try to unify that with this thingy right here. By the way, this right here should not use the equal, but should actually like compare the types on a semantic level. Okay. Here we used to do that. This is like not the most readable code to be fair, but this should return, maybe map one string to yogurt. And assignable to because it's plural. Yogurts and eggs, maybe. If it doesn't work, then this is just none of that. Else it's the environment. Okay. Oh yeah, I can also invert that. If it works, then it's the environment, else we return none. Okay, so in here, things get easier and more and like way more readable. We check are they the same length. Can also assert that in here. Panic, yeah, that's fine. or we continue, and then we try to check that they are assignable to that. So args are assignable to some params, boom, or continue. It's generally weird that this returns a map and that this returns a map and not just a bool, because the name is assignable and is assignable. Like, I should do some refactoring for this, for sure. But now you really see this like parallel structure. We have this name matches, then the full matches, and in each of them we just continue if something doesn't match. Okay, cool. Okay. Then what do we do? Fun is not in scope. That may be true. Because this will just be yogurts. And this will be x.lamp. Okay. Result.env is not here. 270. And yogurt. Okay, here we have concrete arguments. Concrete parameters. So let's maybe env is fun. Yeah, the concrete param types maybe is list of yogurt type, and for param in params do param types dot push the type. You can switch this, and there's the case of time. And runtime. And then we check param types. Assignable to the egg.fun marks. Egg.fun param types or something like that. What do we do down here? We have a call. We just look that up. Oh, I see. How does the lookup work again? It takes the fun.params. Okay. Fun.params. That's it. And this should work, because otherwise this toYogurt function wouldn't have been called. Because we only, like, first, when we encounter a call, we first look for a matching function, and only then do we compile that function. So we know that these parameters that we get, they match the parameter types of the egg fun. Oh yeah, I can just do unwrap. Okay, so we have a type environment, and then claimed return type is egg fun. Return type, yeah, specialized with that environment. Actual return type is, you know, from the function code. So fun dot, what does it have again? Expressions. Dot get fun dot body dot returns. Oh, can you get something on a function, right? Like this. Yeah. And this, now we have the type. And now we basically want to check that those are the same type. So claim return type equals actual return type. Or we panic. Actual types don't return types don't match. Like, you know, claimed type is something. It's the claimed return type. And let's maybe split this like this. Yes. And then we have the actual type is the actual return type. Okay. Yogurt type, yogurt expression. Why is this? Oh, makes sense. We get the expression and the expression has a type. These work or don't work, but give me a useful error. There should be a type error. Yes. Yes, look at this. Okay, so we have the function and we saw that the function returns something weird. It claims it returns a list, which is an enum that is either empty or more with some other stuff. But actually it returns this, which is an enum with either empty or more with an enum that is either this. And like we as humans, we know that these are the same type. But the compiler complains because it can't figure that out yet. Okay. Okay. This is nice. This is very nice. So now we get to actually comparing types, I guess. So we have joining types. Yeah. Let's do that here. Comparing types. Multiple types may describe the same set of values. For example, these two types semantically equivalent, and like first is an enum containing A but nothing, or B, which is recursive. Second is an enum that is either A with nothing, or B containing an enum that is either A or B being recursive with this. Nice. Let's try to operate like this maybe. You know, like they are kind of like equivalently equal, kind of equal. Okay, yogurt type. B yogurt type. And this just returns a bool. Nice. And what it does is, I mean, first it switches on the type. That's like that's the obvious thing. So we switch on A. If it's an int, then if B is int, then we return true, else false. Right. We can just say this, much easier. Never is the same if B is also never. Yeah. Cool. Now we get to enums. So we have an enum with A variance. It's only the same if B is also an enum. So let's just say b.enum or return false. Like this. Yeah, now we basically need to check that they have the same variance. So a variance dot len on hash maps, I'm not sure. Hopefully this works. Oh, I see, we don't have any type checking because this is not actually used yet. So let's use the operator. Yes, because I think this is called size on maps. Otherwise, we go over all the A variants, which is sufficient because we know that they have the same length. So if there were some mismatches, then we will directly know that here. A variant do not B variant is B variance dot get A variant dot key or return false. They are not the same because the enums mismatched. Okay, so then we have the B variant. And now we want to check if they are the same, which means we basically call that recursively. Oh wait, but they are slices. So for both in zip A variant with value dot iter, I guess, and B variant with value dot iter, we just check that both dot A equals, approximately equals, is equivalent to both dot B or return false. And if that works, we just return true. And recursive types should I see. Yeah, here we can't extend, like we can't, for example, in this case, in this case, we can't just check, well, is recursive type 1 equivalent to this? Because recursive type 1 is not a self-contained type. So we need to extend the types before. A dot extend 1 level. And same for B. Checking if A and B are equivalent. Cool. B variant dot value does not exist because that is a slice for some reason. That makes sense. Well, okay, I guess. B args. Args is a variable value, and then we can say A args.iter equals B args.iter. Okay, cool. Let's see what happens. This should, oh, interesting. Zip edges have unequal length. Why is that? Oh, because of this. No, this doesn't make any sense. So why does that happen? Let's see. Checking if these are equivalent. I mean, that's already like super weird. Oh, but this works. Checking if true or false are equivalent, if ints are equivalent. Yeah, checking if what is this type? Where does that even like what? Why? Why does that happen? Insert cast from this to this. Sure. Insert cast from this to this. No. Oh, yeah, no, this is correct. Yeah. So joining, I think joining returns empty or more int with an enum that's either empty or more. Okay, that seems correct. But then there's checking if they are equivalent. Oh. Maybe before we do that, I'll just print checking return types. Return type. Yeah. Okay. Yeah, this is correct. Claim type is this. Actual type is this. And then we're checking if this correct. And this, if these are equivalent. So because these should be equivalent, we then check that ints are equivalent, checking if int and int are equivalent. Yes, they are, probably. Oh, I see. And then we check this and this. And apparently, for some reason, this gets evaluated to this, which is not correct. But still, this should not happen. Like, we should catch that. So let's maybe do that in here. Yes. A args.len equals b args.len or return false. Great. Yeah, return types don't match. Yeah, and this should work because this should expand to this, not to this. So this extend one level or something is not working correctly. Oh, which I feared. Yeah. Okay, so let's see. We have an enum. But we, now this is not abstract. Now we have this concrete example. We have an enum. True. And new variants is what we want to do. So for each variant, we put here the key and we map the value. Okay, so for example, for the empty variant, we push something where the key is empty and the value is something. Right, so here we have the arguments, which are empty for now. And these actually should remain empty. Wait, what? Yeah, okay, let's look at the more variant maybe. Okay, so we have the more variant. And we go over all of the arguments and push something. That is correct. Yeah, same number of arguments, what we want. Okay, actually let's log this. Let's say extending one level. And then switch type, we have different stuff. And this is actually like of our result. This is only for debugging. Later I'll remove that. Extended. Yeah. Okay, so we are extending this so that you can actually navigate into this. Because if you navigate into this, and you look at int and you look at this doesn't make any sense. So this gets extended into this, and this is like clearly wrong. We don't want to have empty with something inside. So yeah, we have an argument, which is in this case this argument. Okay, so in here we put something. And to do that, we first build an extension for the type. And the extension is just an enum, which again is correct. This should be replaced with an enum. That is correct. With some variants. Sure. And the variance of that should also be true or false.
Also correct. Yeah, the question's only what are the arguments of those. And this is where things go wrong. So if the, we're currently looking at the more variant. So if the so for the more variant, oh, should be like this, right? Yeah. Yeah, we are currently in the more variant, and currently all other things, like for example the empty variant, they would just get the payload of the more variant, which is incorrect. They should get their own payload. Let's look at this. Oh, yeah, this is expected. Okay, nice. Okay, yeah. So we check, are these types the same? We don't know. In order to figure that out, we just extend this type one level, and the extended type is this. Correct. And same with the other type here, which is coincidentally the exact same type. And then we check that the ints are equivalent. Yeah, we check that the other types are equivalent, and because this is a recursive type, this will take forever. Nice. Yeah, so in order to fix that, we should also have like a stack of types that we are currently comparing. Yeah, let's maybe currently comparing is list of yogurt types. And then, we still have the simple signature too, which just calls, which should call this right here. Check is equivalent to A dot is equivalent to B with an empty list. Yeah. And then in here, before we check any of that, we just check if currently comparing, which by the way should be a list of tuples. So elegant. Oh man. Yeah, we basically want to check, does that contain the tuple then B. Then we return true. And this doesn't work because I think iter has a contains method. Mutable iter. Yeah. Okay. Oh. Tuple 2 of... No way, tuples don't have equality checking. Let's fix that. So let's look at the Martinez standard library, and there are probably, yeah, tuples. Crazy. Okay.
can write tuples. We can equate tuples. So we have a tuple 2. So let's say A, B. We have tuple 2 of A and B, and tuple B of A and B. And we want to check, are they the same? We should be able to just check A.A equals B.A. and A.B equals B.B. Okay, yeah, expected, because we don't, like, we never add anything to this list. Yeah, so instead of like returning, you know, here we call ourselves recursively. So I think we just need to like currently comparing dot push a tuple like yeah, let's maybe do that up here. Currently comparing the push. And then we need to do the equivalent down here where we say pop something. But basically we need to do that before every single return. Maybe have a it's kind of, let's add another function. Another function, yeah, is equivalent to logic. And that basically only contains this. And yeah, this is like unreachable. Cool. And this calls, oh, no, this calls is equivalent. Both dot A is equivalent to both dot B, given the currently comparing stuff. Yeah, perfect. And this then just calls A dot is equivalent to logic. Yeah, let's maybe just call this is equivalent. I think that's clean, because this also doesn't like read very well. So working with just function calls. Is equivalent A and B using the thing we are currently comparing. Yeah, like that. Is equivalent logic of A and B and currently comparing. Then we pop that. And then we return the result. Nice. Yeah. And let's just make that like this. Cool. Oh yeah, this should be like a mutable list. It should do that. And same here, right? Currently comparing mutable list. And we don't need this. And this. Nice. Okay, I like that. Let's see. Whoa, something happened. Oh, something weird happened. Ooh. Okay, so let's walk through this, I guess. At some point, we join these types, sure. And then we want to check the return type. The claimed type is this, and the actual type is this. And even that's fine if both types are equivalent. So we check, are they equivalent? Which means we take the left side and extend that one level, which means this. And we take, so we get this, and then we extend the right side one level, which is this. The same, because it doesn't actually like reference the root type. And then we dig down, we compare the empty variants, they don't have any payload. We compare the more variants, they have ints as payload. So are ints equal? Yeah, it turns out they are equal. And then they also have this right here as a payload, which means now we check, is this and this the same? Which, by the way, we haven't done before. We have done this and this huge type, but not these two types. So we do that. We extend this one level, we extend this one level, checking if ints are the same, and then, ooh, yeah, and then we are done. I think this works. It returns true because they are the same type. And then we check the return type of something, but return types don't match. Int and empty. Int and a list. Wait, that may actually be the case. Oh, yes. Because the main function claims it returns an int, but it's actually returning a list. What? I mean, that's pretty amazing. That is amazing. What? Okay. Wow. 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 Cool. I guess. Yeah, I guess we should. Okay, I mean, we have navigating types. We have comparing types. Next would be joining types. That's done down here, but it doesn't work right now correctly for, oh wait, maybe it does work correctly. Probably does. What? Yeah, checking if types are assignable. We need to do that. But like the main parts in here, they are done. Let's write a more complicated program. Let's say we make a list of the length A. That is our list. And then we say we want to get the length of that. And let's do that. What? Yeah, we can get something from a list, which we can't really, which is kind of sad. Yeah, let's, I think I'll just actually write some code. Oh. So yeah, we have, let's like organize this. Oh, we don't have comments yet, which makes things a bit tricky. So we have integer stuff up here. So then we have bools. And do we have any? Yeah, we have not. That works in bools. Sure, have that here. Then we have maybe, and we don't have anything that works on maybe yet, but that's fine. We have a list, and then we have a constructor, kind of like a list that takes an item, A, of the type T, returns a list of T, returns a more. And we have a list that contains two items, A and B, returns a list because it returns more, more B, empty. And that's maybe a 3-list thing, but that's it. Right. Yeah, I can do list B. Yeah, I can do list B, C. What? Okay. Okay. So now you should be able to do something like this. List 1, 2, 3. Boom. We have a list. What? Okay. A list containing 1, 2, and 3. Next, getting an item from a list. Yeah, this nonsense. And this, like, really, this, I'm gonna leave it here for just for fun, like, but no. Okay, getting an item from a list. That should not return 5, but basically it should. Get maybe. Oh, and it returns maybe. Oh, okay. Let's look at the list. Like this. If it's an empty list, then we can't find the item. So then we just return none. By the way, this returns maybe T. And if it's not an empty list, so some item and the rest of the list, so more containing the item and the rest of the list, then we want to check, is the index 0? If so, then this is just sum with the item. If it's not 0, then we call ourselves recursively get maybe with the rest of the list. Or even we don't have pipes yet. Okay. So get maybe with the rest of the list. The index -1 and yeah, that's it. What? Okay. Maybe even before that, let's do something simpler. The length of a list. So we have a list, and this just returns an int. If the list is empty, it returns 0. If it's more with an item and the rest, it returns basically the length of the rest. And +1. Yeah. So let's just say we return the length of them. Like, lots of stuff will not be working. Yeah, okay. Yeah, that's what I thought. Okay, so this is additional garbage on line 36. Wait, line with A and B. All right, yeah, we don't have. Who am I to use parentheses? And equals, that's like advanced stuff. We only have indentation for now, I guess. Yeah. Oh man, I should really like add some of these little syntax things that make writing code way more convenient. Okay, expected equals. That doesn't tell us anything. Nothing. Oh, but I know. Yes. The usual error. Yeah. Okay. Oh, and I mean, this won't work. You need to, okay, maybe with the rest and the result of calling minus with the index and 1. Whoa. Whoa. Okay. Okay. Checking if these are equivalent. Oh, yes. The list constructor containing like list of A, this right here, it returns a more of int and empty. And obviously that's not the same as a list of T. But list of T is more general. This is assignable to that other type. So we need to use this function right here. Assignability. Types are really just sets of values. One type is considered to be assignable to another type if all values of the first type are also values of the second type is assignable to. Yeah. I mean, this is really elegant, and this should be like this. Yeah. We join the types, and then we check is the result still the target type. Okay, yeah, I like that. Right, and we need to use that in when checking the function return value, I guess. So return, yeah, this right here. We don't need this, I think. And in here the actual is assignable to range return value. Nice. This call doesn't work. This assignable to this. Wait, maybe your type join. Oh. Oh yeah, if they can't be joined, like that's yeah. If they can't be joined, then it's also definitely not assignable to the other. Whoa. Okay. Where what okay, so there is some stuff happening. We are joining a type and another type. Oh, right. Yeah, we join these two types And yeah, we also need to track the recursive types that we are currently joining, similar to how we do that for the equality. For the equality, we have this list of which types are we currently comparing. And yeah, and here we need to do something similar. We like, okay, this makes sense. Yeah, when we join two types, yeah, when we then recursively join types, we need to know which types we are currently joining. So joining A and B, and an empty list of these beautiful tuples. Yeah. This doesn't work because this has to be a reference to the list because it's an immutable list. Okay. Cool. Right. I mean, this should be very similar to what we do up here, right? So basically, we do this, and then we do. Probably it does make sense to have like a. Yeah. So here we have return none in some places. Okay. No problem. No problem. Currently joining, if that contains these types, then return some to do. Yeah, and then it says basically this, joining these two types. Currently joining, we push the types, we extend them to one level, we join, we call the actual join logic, we pop them, and we return the result. Okay, I like that. So then we can focus on the actual join logic here. Join logic. And we don't need this anymore because they have been extended up here. Okay. Yeah, and this is unreachable because while we are navigating into the types, they are always extended at the bottom. Yeah, but we can only join enums with other enums, right? So let's actually like do b variance equals b dot enum or return the clips. Yeah, and then we can de-indent this. Oh, okay. Nice. And now the Cool. Cool. Yeah. Now there's this to do. So I think this also needs the depth that we're currently at. Like, you know, compared to, oh, no, it doesn't. Ooh. We are currently joining types that have been joined before and contains, is there also like a find or something that returns, yeah, is some position? Does it return the position? Yeah, I don't have, like type ins or stuff like that would be super useful. You see, this is also like, maybe of never should be assignable to maybe of yoga type. This type system is it's safe, but it could be more lenient in some cases, I think. So yeah, now we get an interesting error. The actual is the position in the list. And I guess what we really want to know is how many levels do we need to recurse up? And that's just level is currently joining a len minus the index. So this will be yoga type recursive of that level. Let's see. Nope. Okay, so what's going on here? We are joining these types. Fair. That makes sense, I think. Then we are extending the left type one level, the right type one level. We're joining the ints, sure. And then we're joining the other thingy. Oh, it doesn't call itself recursively, does it? It's called join with this, and then in here we say we have the variance, and then here we have this evil call to the outermost join, which then creates an empty list and so on. So here we actually need to wait, b variance, yeah. We want to build some common variance, and if it's already in there, before we do this, we also need to check that the var bmax, is variant.value. Let's do that up here. If we want to, I don't know. Yeah, we can do this. We can do this. We can do this. We can do this. Key, and then these can just become key. This is b args. Okay, we have the key and we have the args. Okay, maybe keys, some a args. Yeah, we want to join them. Before we do that, we need to check that they are the same length, so that a args.len equals b args.len, or we return none yoga type. And then we join them. And again, in here, we can just say b args. Nice. We join a args and b args by calling join with these and currently join. Beautiful. Actually beautiful. Yeah. Ooh. Ooh, yes. I see that in both cases, it just does this. So let's actually unify that into something like this. Here it just returns these, and otherwise it's just the b args. Yo, this is clean. Very, very clean. Assembling. Okay, to do, interesting, is assignable to yogurt type egg type. This right here, I think. Yeah, this right here, yogurt type egg type. And here's a to do, let's guess, in the recursive type. Ooh, wait. So this is matching on the egg type. The egg type is a oh. All of this was for yogurt types. But of course, we somehow need to do something similar for egg types, I guess. Yeah, we need to be able to navigate down into egg types. We need to be able to compare to egg types. Back to egg types, yeah. We need to be able to check if a yogurt type is assignable to an egg type. Oh, I don't like that. I mean, really, what's the difference between? Yeah, okay, there is a difference. Yeah, egg type is just oh wait, egg types also have like calls and stuff inside of them. So yeah, egg types. You can't really. No wait, egg types don't have calls. Nope, they have recursive. They have recursive types. And there are already int and string and never and so on. Wait, the only difference between yogurt type and egg type is that yogurt type doesn't have like a, you know, a this right here, the variable. I think I think we can unify stuff. And in particular, we can do that because all of these types, they behave exactly the same for, like type, checking types for equality, joining types, checking if types are assignable, all of that. These are just like these variants are treated like concrete types that are only equal and joinable and assignable to themselves and nothing else. So I think we can actually join them into one, I don't know, named type maybe. Yeah, one named type, and then we can, we have type variables which are lowercase, and that we have an uppercase int and string and type, and if
later on we add other built-ins, or we remove string in favor of a custom buffer thing or something, we can do that in there. We have a concrete named type. So I'm proposing like primitive type, not necessarily built in, but like this. And type variables are treated like primitive types. They are primitive types. Type and built-in types are also primitive types, but they are just, we don't need to handle them differently, which actually is a lot more elegant, I think. Yeah, because I mean, look at this. Here we have type algos. Yeah, all this, like all of the primitive types, like int and string. Here they just map to themselves. Here they check if the other type is exactly the same. Like the interesting part is in these enums and recursive and never types. Yeah, these types, they are all treated the same. They're not special in this case. Same here. Same here. So joining types. Yeah, yes, never is treated differently and so on, but all of these, I mean, come on, let's unify that. So then I guess the yogurt stage doesn't actually have their own type representation. Like I think we have one, like this type representation, which is common across the yogurt and egg stage. Except that in the egg stage, the primitive can also be a lowercase type variable. And in the yogurt stage, we know that this is only like uppercase concrete type stuff. But that's more like an implementation detail or something. It's more like that than anything else. Okay, so let's I guess remove the yogurt type and just use the egg type everywhere. Should we call it like something more general, like breakfast type, maybe? Oh, then we could also move it into type algo, like have one module for like the type and type stuff. And then these compiler stages, they just make use of this type. Actually, I like that. Yeah, let's do that. Let's do that. So instead of an egg type, we just have type dogma. Yeah. And this contains a new creation called BreakfastType. We can't just use type because the Martini standard lib also contains the type definition. And we don't have namespaces and scoping, and you know the deal. Okay, so BreakfastType. Here it is. Yeah, and this basically implements the entire like type system. One of the egg type stuff in here just gets converted into breakfast type. And yeah, we should import that in here, type. And I'm
there will be lots of errors. I'm not sure why they aren't shown. So let's just try to compile this, I guess. Is assignable to refers to egg type. And here, true is assignable to breakfast type. And like you may think, oh no, now we're making the language less type safe, you know. And that's true. We are making it less type safe. Like we don't include at the type level whether a type can contain variables or not. That does make things less type safe. But at some point you have to it's a trade-off. What do you want to code in your type system? You could also say, well, the division can fail if the dividend is 0, so it should always return maybe of int or something. But that's not practical. And I think in a similar way here, it's a lot more easy to just rely on convention when saying, well, this type can contain type variables, this one cannot. It's much easier to enforce that with a convention rather than duplicating those types in the type system. And actually, I think in, if you look at, I think maybe with breakfast, this would actually be easier because you could have a function that works on both breakfast and yogurt types. It just takes, it can take an enum with a type variable inside, even if that's never instantiated, if it's never used. So yeah, so here we'll just have one breakfast type, and then we don't have these, but instead we just have primitive. Yes. Now we need to check, is this lowercase or uppercase? Which, to be honest, is kind of hacky. That it, it's still at this compiler stage. We still we distinguish between that. Yeah. I mean, the other option would be to have just a generic type. But that's also, no, you don't want to do that. You really don't want to do that. So let's just say this is a primitive type with name. And then basically if name dot chars get 0 is uppercase, then we do this. Else we return this. And yeah, actually the case for then will be just to check whether the name is the same for the other type. Yeah, instead of naming it concrete and yogurt and egg, let's name it the concrete and generic. So we have a concrete type,
and a generic type. Nice. Nice, nice, nice. Yeah. Is type variable is yeah, something like this. Nice. Okay. Yeah. And then these don't exist. Oh wait, if if concrete is primitive concrete name and this is generic name, yeah. If the concrete type is also a primitive type, yeah, let's maybe say concrete dot concrete name equals concrete dot primitive, or written this, and then let's say if concrete name equals generic name. Yeah. Yeah. Okay. Perfect. And then we can remove all of this. The never type means that if the generic type that we want to assign to is never, yeah, it can only be never. Only never is allowed. Yeah. Wait a minute. Wait. Never is assignable to anything. So we also need to check if concrete is never, then just return, some map. Like this. Yeah, this should work. It does work like this. And this as well. Okay, perfect. This is not really, we don't have two types. Like we do have two types, but they are not the same level of level of type. One is concrete, the other is generic. So rather than checking is assignable to, I think we should rather check something like matches or something like that, or like match. Match against. We have a concrete type and we can match that against a generic type, and that gives us a maybe of stuff. Yeah, I like that. Yeah, and this right here is surprising. I would just say it doesn't match in that case, right? Yeah. Cool. So we have the primitive thing, we have never, we have enum, and let me just review this. So we have a concrete,
a generic variance. We have concrete variance.
Yeah, if that's not an enum type, then it doesn't match. We have a mapping. Oh, this is like the environment, right? Arc mapping, and then, yeah, this is, wait, this is like exactly what we do down here. Am I crazy? Like, we check if both are the same length. And then we like check, hey, this should all match in a single environment. But okay, let's specialize, but okay, let's maybe
refactor this so that instead of having a map in here that we like pass around everywhere, let's just say that we collect the matchings somewhere. Yeah. Let's say we have this match against concrete generic, and this just returns you a matching or match substitutions, match substitutions, something like this, yeah. And that's really just a struct that
contains
a map that contains exactly this. A mapping from type variables to concrete types that they need to be replaced with. Perfect. Yeah, okay. Yeah, we have that as well. It's just both exist. Okay, so we can match types. It's actually matching types. So, heading matching types. Checks if a concrete type is assignable to a generic type. If a concrete type without type variables is assignable to a generic type that possibly contains type variables. Returns a substitution map of what concrete types the type variables need to have for the mapping. For the types to match. Okay. I don't know, that, yeah, still weird, but better than the default. Okay. Cool. Right. Yeah, actually, I think the like for error reporting, it would be so much cooler if we could say, hey, in order for this to match, t would have to be int and string at the same time, something like that. So maybe we don't really want a map of substitutions, but a list, maybe. Yeah. Oh, but maybe. Yeah. I'm going to match substitutions. Perfect. Yeah. Let's just call this substitutions because why not? Type variable strength, and then we want to just collect them. Constraints is a list of tuples in string breakfast type, like this. And yeah. Okay, yeah. And this at some point will probably return a result of either like substitutions or some reason explaining why the types don't match. That's nice. Okay, so match against is defined up here, and then this is like a recursive definition with a concrete type, a generic type, and then we have constraints, which is immutable type variable constraints thingy. And what this does is it matches this type against that, but then it just adds all constraints here, even if we have conflicting constraints. If we try to assign a map from string to int to a map from t to t, the constraints will have, this will like work, it won't return anything, and the map will just contain, the constraints will just contain the constraint that t has to be string and t has to be int, which is conflicting, but we collect them anyway. Okay, so the concrete type, if it's never, then yeah, that works. We can just return. If the generic type, yeah, we switch over the generic type. We check, is this a type variable? If so, then we want to add a constraint. Oh, yeah, this should return a bool. Yeah, because it may be that we just have completely different types, you know, string to int. And that's not, that doesn't match because there would have to be conflicting substitutions for variables. It fails on a more fundamental level. The structure of the types doesn't even match, not just looking at the substitutions. Okay, so yeah, this returns a bool, and in this case it just returns bool because it works either way. If this is a thing, then we add a substitution. So I guess constraints dot add comment. Oh, nice. Constraints dot push tuple from v to concrete. Okay, and then we return. Sure, yeah, this worked. We don't even need to return that, we can just evaluate to that. Otherwise, we need to check that they are the same type. This right here. If this is not a concrete, if the concrete type is not a primitive, then we just return false. Otherwise, oh, look at this. We just return that they are the same. This is so much nicer. Oh, same here. Case never. Well, concrete has to be never. Boom. That's it. Okay. Okay. Yeah, concrete variance is like, if that doesn't work, yeah. If this is not an enum, then it doesn't work. Here we have a mapping. I mean, sure. Does that work? How does the generic thing work? Okay, no. Well, okay, so we do this. We have concrete variants, concrete arguments, generic arguments. If that doesn't work, then the lengths have to match. And the argument mapping has to be assignable to, which is more like match against, plus yeah, a dot match against b, and also give in the constraints. Yeah. Yeah, and then the arg mapping, yeah, that's nothing. We don't need that. If there are like obvious things that don't work out, sure, but like choosing concrete mapping is not needed. Okay, otherwise this is just true. Okay, yeah, I like that. If it's recursive, we do other stuff. Sure, match against with slices. And this should also take constraints. Also just returns a bool. And it's basically this. I mean, yeah, we should probably like save this somewhere. Maybe up here. But yeah, basically this just returns false. And I mean, honestly, it does this and matches them. Match against b. Please add your things to the constraints. If that doesn't work, then we return false. Just like this. Boom. Nice. Wow. Okay. Wait, why we don't need to do this? This is basically what we do down here, right? But they have the same length, which we also check here. Yeah, we can just say concrete match against generic marks, please. Add your stuff to the constraints. Nice. Very, very nice. Yeah. Cool. Cool, cool, cool. And then up here, we can just say, let's create this. No. And then we match those types, like complete match against generic using the constraints. No. Yeah. And then we try to build substitutions. Map, yeah, does it work? Let's go over the constraints. Ooh. Yeah, separating this into like a two-step process. First, comparing only the structure of the type, and then checking if the variable substitutions are coherent. That simplifies things so much. Okay, so yeah, here we just check. Yeah, no, we don't check that. Nope. This is basically what we have right now. So we have the constraints, and then we just check if maybe big is constraint dot a generic is constraints dot wait b, but not really concrete, and this is more like the variable. Variable is constraints a, concrete type is constraints dot b, and then basically if we get the variable not env but substitutions, we check that the type matches the concrete type, or we say works as false, we break. Otherwise we put that into the substitutions. Yeah, don't need this because there are no nested things. And if it works, then we have some substitutions, otherwise none, which means no substitutions. What? This is like readable code. Can we even simplify this further, like this part down here? I'm not sure about that. Yeah, these have to only be, you know, this. Okay, I think yeah, let's leave it like this, I guess. But yeah, I still need to like change a lot of things. But the matching of types should work. Oh, right. And now we can actually like do the thing that we wanted to, which is that when we navigate down into the types, you know, down here, it's never return much. No, 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 no. Yeah, we also need to let's just get this to a working state and then continue figuring things out. So navigating into types, extend one level with a breakfast type. Okay, this should all work. The problem is only, yeah, when we interact with the other compiler stages. So this has a name, params, return type, and then the actual implementation. Sure. Down here, we create, oh, no, no. How do we do this? Wait, I thought we had some, you know, ordering stuff somewhere. No, we don't. Okay, let's just add some type definitions for common types, you know. Our type int is breakfast type dot primitive int. String is just a string. Type is type. What else did we have? We had ordering. Oh, but it's not primitive types, it's an enum type with map from string to slice, or from string less to a slice, which will create using. It's kind of inconsistent that slice has the empty prefix, but yeah, should be able to say slice. Maybe I'll fix that. Some equals and greater. Okay, so we have these types, and then here we can just say type int. And this is type ordering. Yeah, look at that. This is string. Yeah. Actually, let's define type never here as well. Yeah, primitives type never is just breakfast type dot never. Constant. Oh yeah, type. What's the type info? I think. Type info is this with int string type enum. Int string type enum. Cool. Yeah. Okay. Yeah, type does maps type to type info. Type info. Oh, beautiful. I mean, honestly, this is. Oh yeah, I'm just gonna say type name. Wow. These are the signatures. Very, very cool. Okay, so ongoing calls, we have a variable. Yeah, that's just a primitive with the variable as its name. In here, we return string, which will be type string. Oh, type int. Oh yeah, type. Cool. Let's check where this breaks. Standard match. Okay, so obviously there are some things that, oh yeah, this, we don't need that. Nah. Boom. Gone. Okay, compiler type only has these variants. There is no int. Right, all the things get easier. Yeah, no. This is just it's some primitive a, and b is some primitive b. Then we just check if they are equal. Otherwise, nothing to do. Sure. Okay, this is not a variant case variable. True. In the egg, right. Yeah. Like this. There are no definitions named are assignable to. That is good. Because that's a horrible name if it returns a map. Yeah, for the functions, we just save the substitutions, which is a much better name than environment. And we match them against the parameters. Oh, right. But those are multiple, so we need to add that as well. We need to basically something like this. Yeah. So maybe add a function. Or check coherency of constraints. And it returns immediately. This, like, just from the signature of this function, you can see that this makes sense. We have matched those types, collected constraints, and now we want to check whether they are coherent. And that maybe gives us some substitutions or it fails. Nice. Nice. Really, really nice. So yeah, constraints dot check coherency. And now we basically want to have a very similar function for slices of types. Which again is just going to create this. Yeah, let me add a function from it as well. I think today I'm in the refactoring mood. Type variable constraints. Yeah, it just does this. Nothing surprising there. Okay.
So yeah, this really just creates things, matches them, checks the coherency, and it's the exact same thing in here. Nice. Okay. So where does it fail now? Match against. This call doesn't work. Slice of yogurt type. What is yogurt type? Oh no. We still have the yogurt type. No. Just remove that. Yeah. Yogurt param with a breakfast type. Yeah, egg lookup result. Oh no, it won't contain this. It will contain substitutions. Nice. And then it's gonna say match them, giving me substitutions. And yeah. Now this fails. Yogurt value type. Yeah, that doesn't. Oh, yogurt value. Oh, I say yogurt value type of a breakfast type. Oh, I see. Yeah, what? Yeah, the types are no longer really needed, right? But yeah, like each instance of yogurt type will just be breakfast type. Okay. Sure. Okay, yogurt fun builder and other stuff. This will, oh, now we're at the C level. So here we mangle a breakfast tea. Yeah, I think it does. Writing a breakfast type because it's probably defined in the yogurt, isn't it? Yogurt, write body, write fun, write the type. Yeah, don't need this. Is there like a write function in here? No, not really, but there should be. Where is the other write function? Because this looks like, you know, a good write function, like the one we just adjusted earlier today. Yeah, but the primitive, you just write the name. Oops. Yeah. So the question becomes, we're gonna look at that later. Matching types, match against. Yeah. And after matching types, you usually specialize types, and then you do other stuff. Okay, so let's see. This call matches multiple functions, but I don't know where they are. Right. Okay, so there are these write functions with bacon stuff, blah, 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 here, breakfast type, which is actually implemented correctly as well. Okay, but let's remove that here. And in the yogurt, we don't have that anymore. Yeah, because now there's only in the type file. This thing. Okay. Yeah, to yogurt. Compiler yogurt. Dot int. No, this is just int. Oh, and by the way, this is type string. And this is type. Okay, and this fits in one line, also nice. We have this. Okay. Constraint is not in scope. Compiler type. And like 148. Down here. We match some types. Okay, constraints is uppercase. Doesn't exist. Okay. That is surprising to me. Is uppercase letter, maybe? Let's maybe open up the standard lib for strings and characters. Here is upper, not is uppercase. Sure. V is not in scope. 1, 2, 3 here. Push. Oh yeah, the name is that. Okay. Maybe string and string. That doesn't seem right. Oh no. Yeah. 104. Let me see. A is not a field on type variable constraints because this should be constraint singular. This is not a variable in type. True. These are all primitive types, just on themselves. They don't need to be extended. And the same goes for extending them again. Yeah, and for here, replacing the recursive level. And down here, checking if they are equivalent. Yeah, they basically need to have the same name. B.primitive or return false. Okay. True. Yeah, here we actually need to create the substitutions script. Substitutions field is missing. Yes, it is. In the egg lookup result. which is in the yogurt, I think. Yeah. Type. Join logic. Yeah, primitive types need to match exactly. A name. If B is primitive with a B name, then stuff. Yeah, let's just do this nicely. B dot primitive on return this, and then we say a name equals B name, or return this. Then we have this primitive with the name. Okay. So then yogurt 393. And was not a field. Wait, what? Yogurt. Here. Result dot substitution. Specialize. Oh yeah, specialize needs to take substitutions, which makes total sense. We have like some sort of type safety across these boundaries. Yeah, specialize here. Takes substitutions, which are just substitutions. We switch on the type if it's a primitive. We say, well, what do we say? Substitutions. But substitutions that may be variable. Yeah, that's a concrete type. Or if that doesn't work, then we just say it's a breakfast type dot primitive with that name. Cool. Yeah, these don't exist. Cool. Very, very cool. Yogurt type ordering. No, that doesn't exist. Because it's simpler. It's just type ordering. And that's the only remaining yogurt type thing. Let's see, case int what? 513. Yeah. Type info. Oh. Yeah, no, we can just say if it's a primitive type. It's just in string type, yeah.
There are no definitions named are assignable to. There are not. Okay. That makes sense. Yogurt. This should match types. Yeah, check that the return type matches what the function claims it is. So get the parent types, and then we match them. Oh yeah, match against these, giving us substitutions, and then specialize the return type using the substitutions. We're getting there. Yeah, exactly. So primitive type. Basically in here we can then check if name equals n. Then we just run the bracket. Right. Okay. Wait, this is the mangle. Yeah, the mangling. Okay, yeah. Okay, I mean, in that case, we can just write the name. Sure. No problem. Yeah, this is the actually interesting part. So if it's a primitive type with this name, then we want to switch. We can't switch on these, but we want to check is the name int. Then we do this. Else, if the name is string, then we do this. Else, if the name is type, then we do this. Else, to do primitive. Cool. Primitive name. Yeah, this, we don't need that, I guess. Sure. Yeah. Yeah, casting only works for ints. World. Okay, so these types don't match. Return types don't match. Oh, the claimed type is this. But the claimed type here, the t should be replaced with an int. Ooh. No. Like, I mean, this is nice. Really, really nice. But then these. I guess. I don't like how this is extending t one level. Why joining int and t? So we call list. I get that. So then we have, there has to be some yeah, that's actually like print, hey, we are compiling a function. Just debug that to your good with an egg fun. And we have the signature, and then we'll just print compiling. Cool. Oh, okay, so compiling main int makes sense. Compiling list. Okay, yeah. Then we maybe like this. Yeah. Let's do this. Okay, so compiling, no, but we're already compiling that. Okay, so compiling list of 3. Makes sense, I think. Compiling a list of 3. Let's say a list of 3 should return a list of int. Oh, yeah, this returns more of int and empty. True. And the return type is supposed to be this. Hang on, the return type should doesn't really look specialized. So we take the parent types, we match them against this. Let's checking return type. Yeah, checking return type. Claimed is this. What? Claimed is this. Substitutions. Oh, sub. I just want to see them. Oh, and no substitutions. That's not good. Okay, so match against doesn't really work correctly. Match against. We have constraints. We match the concrete type against the generic type. Yeah. Matched constraints, and then I would want to see the constraints. .debug. No constraints. Okay, so here we have a tuple. To string, is that breakfast type? Is that? Wait. What's the type of? Like, yeah, I know we compile a list of 3. What's the type of 3? Let's maybe In the signature. Yeah, right here. We will do what? I think it makes sense to yeah, let's just adjust the constructor of that so that it also prints the type. Okay, but the type is correct. 3 of int, which matches some function. Okay. Wow. This is what? That doesn't make any sense. What? Switch. Yeah, this is a primitive type with a generic name. This is exactly the opposite. This is not the case. Okay. Oh, okay. Yeah. Look at all this. Nice. Nice. I guess. Cool. So the program panicked and matched against BreakfastType constraints. Here. That's a to-do. Oh. I don't like that. Okay, so when matching types, we also need to... Oh, we need to handle recursive types. True. So we want to do what? I think we want to... yeah, I think just... I mean, this is like horribly indented. What? Yeah. I think when matching, let's just, in the part where we have two concrete types and we want to match them, let's just extend both. So concrete is concrete.extend level, and generic is generic. Extend one level. Nice. Yes. Yes, that is expected. Because now we need to we need to basically also have this recursive handling of if a type, like to keep track of which types are we currently matching. Yeah, and if something is recursive, then we'll just immediately say, well, this works. So we'll do it like this. Here we have a list. So yeah, right. I'm currently matching, and it's the immutable list of like breakfast type and breakfast type. And then we just say if, actually it's very similar to what we do in join. Very, very similar. Yeah. If that works, if we are currently doing just that, then we just return true. And this just automatically works. Matching page against generic. Currently matching is what it's called. And then we take the concrete type, which is A, and the generic type, and we call match against logic. Okay, yeah. Okay, so this call doesn't work. Because we need the list as well. Currently matching, also need that here. And then in here we can just say currently matching. Match against doesn't work. Okay, so for these we also say currently matching, which we passed in here. Yeah, and now the top level functions don't work anymore because they also need an utilist of tuples. From breakfast type to breakfast type, and a mutable one of that. Generic, and this, and then in here we just have no, not the signature. Signatures, it stays clean. Yeah. Okay. Great. Generic constraints currently matching. Cool. This is okay. Ooh, this doesn't look good. I have no idea what's going on here. No idea. Okay, done compiling this. Sure. Then there's a function call. Yeah, we are done with compiling this function. Next, we want to get the length of that list. Done compiling this function. Now let's look for a length function. A function that matches this signature. So the return type of this, because these are ints, is list of int, which is this in. Okay, and now we have this candidate function. Oh, look, it's called len, takes a list of t. So we need to match this type against this type right here. So we extend both of those types. This type becomes this type, and this type becomes this type. And now we are matching int against t. Yeah, the empty variance, nothing to match there. The more thing we need to match. We need to match int against t, and empty, and this type against this type. So we have int, we have t. Cool. Matched. Oh, okay, this actually, this is nice. This matched. And these are the constraints. Yeah, t must be int for this to work. So then we compile the length function for a specialized signature with the enum. And then we do stuff. Okay, compile that. Why? Matching recursive type 1. That is strange. So when we compile a match, let's see. Switch. Yeah, here. Oh, no, this is writing switch. Yeah, when we compile that, we take the condition, type, we check which variance does it have, True. Then we compile the cases, right? So we say for case in switch.cases variant.args, which is we take the variance of the condition. Okay, so yeah, this is beautifully commented out. Now we lower all the cases. And basically we take the variant value, which is bad. Because right now we want to extend that type. We want to say condition type is this, dot extend one level. Oh, what? Okay. This seems very cool. Very, very cool. let's just... Okay, I see what happened here. So this is nice. So here, this is a list of t. And now instead of rest being this, recursive type, this is inferred to be a list of t again, which is amazing. Yeah. Okay, so now we can call ourselves recursively and the type checks and so on. And now we want to search for a plus function that matches that. Okay, well, we are slowly getting to a working state. But multiple functions match this. That is really multiple functions match plus. It's defined for ints and for strings. Oh no, for strings with string equals int or something. Huh. I'm not sure. Multiple functions match. Why doesn't that like tell me? That's probably in the pure. Multiple functions match this. Full matches larger one. And let me just print a signature, I guess, right? Multiple functions match. Yeah, you know what, let's create a string builder here. We do this, and then in the end, the string. And then there is match, and then for each function. So for each match in full matches, we basically print the match. Like, we print the signature, like the match dot fun, I think. Full matches is a tuple 2 with first the egg fun. Yeah, so the fun name and the fun params and convert it into a yogurt. Well, I guess this is fine. Yeah, these with these substitutions, by the way, and then we print the substitutions. So b dot yeah, that doesn't exist. Closing brace after. Oh, yeah. Should look like this, I guess. Something like this. Okay, yeah. Wait, what? Multiple functions match this. But these, like this function should match, yes. But this function shouldn't. Where's the match again? Okay, so matching primitive types. Is it a type variable? Means is it not uppercase? It is not a type variable. Boom. So yeah, so matching int against string, extend int, extend string, and then matched. Like what? Oh wait. Oh no. Yeah, match against. Oh yeah. It returns true or false. So here we need to handle the false first. We need to say if that doesn't, if the structure of the type doesn't even match, then there's no need to like check the constraints for coherency. What? Okay. So it seems like stuff works. And like this is full matching of recursive types. You can see here we have the len function, which takes an enum that is empty or more, containing an int and recursive thing, and then we switch on that. And if it's more, then we have this to thing, which is an int, but it's never printed anywhere. Well, and this 3 thing, which is like type checked, because this is a recursive type. This is again type checked to this, and then we do then we do overloading based on this. We find the len function again, and here we have plus with ints because this is inferred with int. Okay, this is amazing. We have recursive types. We can join them. We can check them. We can match them against other types. Like we can check if they are assignable, if they are the same. Nice. Very, very nice. Cool. The C code that gets generated probably won't compile. But apart from that, very, very cool. I am gonna take a break, and then we'll probably first do some refactoring of the type file, and then look at C code. All right. Let's just see how the C code fails, but before that, refactor some code. So really, I just want to maybe put a comment in here, reorganize the code in this file, stuff like that. I think this is actually like a good idea to describe the type system. Types in breakfast. So breakfast has a structural type system, which means that types don't have identities. If you define foo equals int and bar equals int, then foo, bar, and int can be used interchangeably. Yeah. All types are self-contained. From the egg compiler. Starting with the egg compiler stage, all types are self-contained, and you don't need any type definitions to resolve, to understand whether some usage of types, and you don't need any type definitions anymore. Yeah. Then there is recursive types. Make some operations these are the operations, the main operations that you usually these are the operations that we can perform on types. Oh yeah, For example, checking whether list int matches a function that accepts a list t. Yeah, we have that. We have specializing types. This results in a specialization. Results in the substitution map t is int. Yeah, specializing types using substitutions. For example, specializing list t using t int to int. Beautiful. Okay, yeah, matching, specialization, navigating into types, comparing types. Maybe describing these up here doesn't really make sense. Yeah, this file contains some of the operations. Most operations that we need to perform on types. And that's it. Yeah. BreakfastType, you can write that, you can match types. You can specialize types. Specializing types. Yeah, it's like have two lines between those sections. Navigating into types. Comparing types. Joining types. Nice. Okay, yeah, that looks fine. Now, I hope this still works. Next would be removing some of the debug prints, like all of this. I'm just gonna look for print line and yeah, no matching thing, please, and not this or this. Oh wait, we can even simplify this further, like this. We have this and this. Okay. Does it still print something? Let's hope not. It does. Checking return type. Oh, but that's in the yogurt. Yeah. Yeah, this is not needed. Cool. Cool. Done compiling and compiling. Yeah, I'm not sure about these, to be honest. I would say, you know, let's keep these for now. Yeah. Yeah. I mean, it is pretty interesting that you can just say, that you can just see, you know, we compile main, we compile list of 1, 2, 3, we compile list of 2 and 3, we compile list of 3, and then we are done with those, and then we compile the length function, compile plus, compile built-in add, and then we're done with those. So this is like a very high level view of what's happening. I like that. Yeah, I mean later on we will remove that, but for now let's leave it in. Okay, yeah, so we have types. Let's let's just commit this, I guess. Oops. Breakfast. What did we do? We now have types. Correct. In the CMAR we adjusted several things. In the egg, well, we removed lots of unnecessary stuff, and types in particular. All the type operations got like extracted into this file. The yogurt became simpler as well, like so much simpler, so much simpler. Yeah, and yeah, these, let's just, I mean, yeah, we can keep that, sure. Okay, I guess support fix type handling, handle types correctly. Yeah, fix types, fix recursive types, fix handling of recursive types. Okay. That being said, recursive types won't work right now. They still won't work, because right now the C code is converted to test.c. And let's just look at that. I'm not 100% sure, but I'm pretty sure that this does not work. Or maybe it does. Wait, what? Okay, so we have this type, which is, I mean, whoa. It has only one variant more, with 2 payloads, an int and this type. Okay, maybe this actually does work. No, it does not. Right, because recursive types are kind of a pain. Yeah. In general, we can't just put recursive types in here. I mean, like, ignoring that, we just write rec in there. But in C, that doesn't work, because what's really happening here is that this struct will have a single memory region where the tag and this union are right next to each other in memory. And in order to know how much space this union needs, it then analyzes these types. So we can't actually represent recursive types in a single C struct. We need to have some pointer interaction in here. You know, something like this is how you write a pointer. Yeah, and I mean, in this case, it doesn't even like make any sense, you know, but still, it's kind of bad. So how do we fix this, is my question. And I guess I would just say, let's okay, we have a set of types. That makes sense. I think. Yeah. And then what we do is we I think we need to handle how do we represent types, like, you know, for each type, if it's a struct. Oh, so if it's an enum, yeah, we just put the content right here. And I think what we really need is a pointer to that, like this. Yeah. Yeah, yeah, yeah. And I mean, at some points, we will need to, it makes sense to not have pointers everywhere, but only when necessary. But until then, this is fine. Oh, right, this, like, of course, for recursive types, we can't just go into the variants and get the value, but instead we need to extend this type to the bottom. So type.mangle is the name, sure. But then we do type equals type.extend one level. Not a, yeah. Okay, yeah, this looks a lot better. So now we have a recursive type that is like actually recursive. You know, our list type is an enum of empty and more of int, and more of, oh, I see, int and recursive one. Sure. Yeah. Cool. Yeah. Next, let's maybe, yeah, that the content of functions will probably not work right here. Oh, 3 is undefined. That's bad. Wait, what? I mean, these are weird errors. Type enum of empty more. Oh, right. So this list returns, like, but list should return type of int empty, and I think right at the end the type should be cast into the part. Oh yeah, that makes sense. You know, in here we check that they are the same. We check the actual support, the actual return type. Okay, yeah, I think I guess we only really need that in the user-defined code. Yeah. Let's put this in here. And then let's add something to the body. yeah. So we get the parent types. Sure, we get the substitutions. We get the claimed return type. The actual return type. Oh, right. And to do that we need the builder. And we get the body.returns type. Yeah. And then if claimed return type is not the same as the actual return type, then we need to make sure that they are still assignable to one another. And we also need to insert a cast into the body. A body with cast equals a list of IDs. And then for each ID in the body, we basically add the ID to the body with cast. But then we also push a yogurt expression. Was it yogurt expression? Dot cast or something like that. What do we do for these branches here? Oh, op was it, right? Yeah, this right here. Like something, we want something like this for the function type. For the claimed return type. Yeah, okay. Mm-hmm. Cool. Mm-hmm. And this returns an ID, right? So we can then do this. If things work the way I think they do. Okay, so this doesn't work because body doesn't have... Is it like this? Yeah. Oh. Actual return type. Oh. I know this is actually body.returns. And that gets converted to the claimed return type. Yeah, this doesn't work because the builder needs to be mutable, I think. Yes. And then we can update the builder. We can say body dot or like builder dot what does the builder contain again? This is not clean. That's not clean. How do we do that in here? We have the cases. We compile all of them. And in each of them is a yogurt body. And then what we do is we get that case. And we have this new return. Oh, and then we just put a new body in there. Right, because the body yeah, body is nothing, body isn't added to the, you know, to the expressions or something. That makes sense, I think. So yeah, body is just body, wait, but then we can just say, wait, body. Just has this, the expressions. Oh yeah, we push all the old. Okay, this is like pretty similar to what we're doing. So let's just copy that up here and then adjust that. Yeah. So the first thing we do is create a new body, which is exactly what we do down here. Then we push all of the expressions from the old subtree, the old body, and then the new return, yeah, is either just a value, which, I mean, sure, but not really like interesting to do. Nice. Yeah, and then we have a builder cast operation that we also want to add, which is exactly what we do here. Okay, and then new expressions, push the new return. Okay, I guess we do that right here. And then finally we do this. We use this as the new body. So really we want here a yogurt body. Oh, I see. Like, you know, this is the cast, basically. The cast that is happening. And then we push the cast. And the body has, you know, params like the old body did. Like the body dot. It has expressions, which is body with cast. We have the returns, which is the cast expression, and that's it. And then we use that as our new stuff. Nice. Okay. Wrote code to test, to see file. Okay, I would say there are less errors at least, which is nice. And let's see. We say, okay, so this is like a list of something. Why don't I, okay, crazy idea. Print the function name in a readable form on top of the function. Crazy. Yeah. I just want the signature. Oh, no. This. No. This. That's it. Wait. Oh, I see. There were two phases for the functions. There's, yeah, the declaration, where we now have signatures, which, I mean, I guess, yeah. But that's not the cool part. That's not where we want signatures. We really want them right here in the function implementations. Yeah, so we have compact declarations, and then we have these function implementations. for example, the len function or the list function. And yeah, this now returns an enum of empty and more of int and recursive 1. Beautiful. And the way it does that is by declaring this and then setting the tag. The tag to 1, yeah, and here we need to also set the payload actually, which doesn't happen for some reason. So I guess the cast expressions are not lowered correctly yet. What do we have here? Identifier 3s. Like, this is super weird. Oh, but I can imagine why. I know. So when we compile a switch for the individual cases, we print a case, and now what we really want is for each of the payloads to be unwrapped. So, you know, like for each payload, for each arc in the switch, in the case dot body dot value dot something, yeah, value, that's the body, I think, and we want to check what are the amount of params that it takes. Yeah. And now we basically want to print that parameter. We want to say, you know, like, we have a parameter here, we want the type mangled, of course, and the param ID. And this should be from, you know, like our initial switch condition. Dot, then the key, dot as dot key, and then yeah, so this is param dot item, and this is the index. Okay, let's see. This is only a yogurt ID, not the actual type, which makes sense, I think. So here we just want the ID, but in here we actually want the expression from the function, like this. Okay. Let's just double check that this works. Okay, so we know this is case 1. Yeah, no need for the underscore here because yeah. And you can see there are 2 payloads, 2 and 3. And they are just switch condition dot mangle as something, but they also need indentation in front of them. So let's add that too. Yes, that's more like it. Okay, so we switch on this enum, on this list enum, and basically we check what's the tag. You know, is this 0? In which case, by the way, we could also like print the name, because why not? Let's make it easy for us to debug this. Yeah, beautiful. And for each, like, I don't know, for each expression, why don't we also write the type after that in an unmangled form, you know? Expression.type, sure. Let's do that. Beautiful. Okay, so yeah, we have this right here, the length function on a list. Yeah, we have a switch and we have an int, which is the length that we want to return. It gets returned down here. And depending on the what kind of variant the argument is, the list argument, we assign different stuff to that length thing. So if this is an empty list, then we create a 0, and then we assign 0 to this. Seems reasonable. If it's the more variant, then we need to actually get the payload. We need to say, okay, I have this, you know, integer 2, which is more, and I have this other enum, which is more 1. By the way, we can also add the types of that here, because why not? Yeah, that would basically be this, which is not like the most efficient use of, well, anyway. I mean, the C backend is kind of horrible anyway. So, okay, yeah, and the payloads of this are an integer, and, well, you know, this is enum. Nice. And this, so the bad thing is that this is not really an integer. It's really a pointer. And what we do in here is we want to unwrap that pointer, I think. We want to say, please dereference that pointer so that we have a concrete value. Yeah, just like this. Okay, perfect. And then, you know, we create an integer, because then we call ourselves recursively on the rest of the list. Correct. We create a new integer, 1, and then we add those two integers. Yeah, that seems correct to me. Cool. Cool. So what's next? I should test this out. That's like the first thing. But the length function looks correct. This doesn't look quite correct, I think. So let's maybe start with the simplest of these. Yeah, here. The list of 3 function. Is this correct? Enum of empty and more of int and recursive. Okay, sure, that's the type of this. And what it does is it takes one integer, it creates a type that is only the empty tag, which means, you know, an enum, and we set the tag to 0. And then we have more of int and empty. So this enum right here, with only one variant, more, containing an int and empty. The one variant is this, more, and then we have inside of that an int, the int that we got passed, correct, and empty. Yeah, and now a tough question is how do we deal with the heap? How do we you know, how do we even, like, we can't just, this right here, this more variant, should be a pointer to an int, and this should be a pointer to an empty thing. And we need those pointers, at least in some cases like this, because these are recursive types. But that means at some point we need to take the reference of something, perhaps. And we can't just take the reference like this. Oops. Because now this will be a pointer that points into the stack. And as soon as we leave this function, this pointer will be invalid. So what we really want is to, for now at least, allocate memory for each object, no, for each value that we have. And I think that makes, I mean, the most sense would probably be to do that centrally. Like, for example, here, yeah. Here we need to basically like malloc memory for the size, for the type. Yeah. Oh, is it like this? I'm not entirely sure. So allocate memory. Whoa. Okay. Yeah, that makes sense. Oh no, and this should be string interpolation. And indeed, this does not make sense because now this is a pointer to that type. And maybe we even need to cast that pointer, I'm not entirely sure. Maybe we do. Type name is not allowed. Wait, how does size of usually look like? I'm not that proficient in Rust. Size of. C. Hang on, let me pop out this single browser tab. Oh yeah, it's written together. Like, of course it is. Cool. I mean, it compiled, I guess. Oh, yeah, look at this. No error to be seen. That is cool. And now can I do like this? Is this, yeah, this is a pointer dereference. Oh no. So really for integers we want this, I think. Yeah, do this. And then in here, instead of setting the data in len directly, we do it like this. Similarly for the enum tag, and similarly here. And here we just take the, the parameters, just that, which is, hang on, we take the switch. Oh yeah, now we don't need that star here because we're just shuffling pointers around. We don't need to dereference that. Okay. Probably, this is probably correct. It's not like I have an entirely, like, totally clear picture what's going on here. But this will probably be fine. Yeah, this will be fine. So yeah, casting something is not supported yet, sure. Instructions, yeah, I'll look at them later. So this is an int pointer. Then we set the pointer to something, which is not at all what we want. What we want is to set wherever the pointer points to that value. Yeah, like that. Exactly like that. Yeah. Also, functions, you know, they return pointers now. Yeah. That's just sad, sad, sad way that things are right now. They return pointers, they accept pointers, everything's on the heap. I mean, for now, I just want to get this to work. You know, it doesn't have to be efficient. I know, it is more efficient than interpreted stuff, but yeah. Okay, so what do we do here? We call this thingy, which accepts type int and type int. That's not what we want, no. We want those to be pointers. Yeah, like this. So this is incompatible apparently, because probably, no, up here this is like exactly the same, isn't it? Oh, these need to be, the parameters need to be pointers as well. Yeah, okay. Ooh, so each time we create a value, we essentially allocate memory for that. And here we just have the function list that takes a 2 and a 3, like it takes 2 integers, which are actually pointers to integers, and then it returns a pointer to this list thingy. Okay, so first it allocates memory for this thing, saves a pointer to that, and then says, hey, this pointer is equal to this, and this should work, because this, again, just returns a pointer. So on the stack we only have pointers. And we pass down this pointer to an int, which is also fair. And then we allocate, yeah, we basically want to wrap that in a more symbol. So we allocate memory for that. Nice. We set the tag to 0, sure. And then we say, hey, down there, this as.more.0 should be this pointer, which works because this is type int star, exactly. And this is, you know, this other struct thing. Okay, yeah, and now we want to cast that. And the way we do that is by switching on the tag. And there was only one option, which is that it's the more tag. Cool. And now we want to, we basically want to cast the yeah, cast the payload as well. Yeah, that makes sense. So let me check how the casting is implemented right now. Cast, yeah. Yes, we say case something, we just set the tag But of course that's not correct, because actually we also want to set the payload. Which means that for each arg in variant dot item dot value, no, let's yeah, okay, item dot value dot len, maybe just like this, probably. We say id mangle dot and then the variant dot name, and then as thingy dot and then the index equals, you know, the source thing. So hang on, we switch on cast. Yeah, dot as dot variant dot item dot key, which I feel like there should be a simpler way to do that, but well, dot underscore arg, like this. And now we should carry over all of the payloads. The payloads themselves, they are not cast actually. Something we will have to look into later. To cast the payloads as well. Yeah, but for now we just say, well, we know that 3 is more with a 0 and 1 in here, and so we set 0 and 1 down here. Beautiful, except it's of course not beautiful because it's all on a single line, so let's add that, let's change that. But that requires indentation. So let me grab this from up here, put that down there, and it should be one more indented than the case. Then we have this, then we have the payloads, which, I mean, it basically just means, oh, hang on, tag equals stuff, yeah, okay. Yeah, for each thingy we print indentation, and then this, and then we print indentation and break. And here should probably not be a space. Okay. Let's look at that. Yeah, almost. Alright, because here is space as well. Yeah, let's turn this into 1 and this into 2, and then this actually looks halfway decent. We know that this is, and again, I want the variant item key. Yeah, if this is a more thing, which is the only thing that it can be because it's an enum with only one variant, then we basically set this to 1, which is the more in that case, in that type. And then we copy the payload. Perfect. Then we return that. That seems correct. And now let's look at the len. So 0 is this, correct? and this is a pointer anyway, yeah. So for switch, the payloads no longer work because this should be a pointer dereference like this. Okay. And now the only error is this, the built-in types, the built-in instructions. They should also dereference the operands. And let's just do that right here and right here. And then in here we'll probably have to, oh no, wait, it's the exact same thing. At least for those up here and for those down there, I'm gonna take another look. Yeah. So here we have, we iterate over stuff. Okay, yeah, we can just use this and this here. Nice. And that indeed worked. Okay. Well, wait, hang on. Okay, yeah, this looks perfectly fine. So now the way that you call this is not by passing this in, because that would just crash everything, because it would turn the argument count into a pointer, which is most certainly unmet in the process virtual address space. So let's instead write a new main function, maybe first in here. So what we really want is something like this, type int argc underscore argc, because why not? That's malloc size of type int. And then we say underscore argc equals argc. And then we call this with underscore argc. Main, yeah, this. Okay, looks fine to me. Let's see if this actually works. Yeah, let's don't save and then reopen that. Yeah, perfect. Okay, now let's actually compile that, I guess. GCC -o test. Oh, hang on, exactly the other way around, like this. Oh. Okay, I mean there are several errors, but they're not shown here. That's okay. Unknown type. Oh, because types are only defined later on. So can you kind of like declare types? See. Oh, sorry. C declare types before usage. I don't have objects or something, but oh yeah, you can just do this. Okay, yeah. We basically know that. Yeah, we'll just do something similar for the types, like we do for the functions right now. First declare all of them, then define all of them, so that the order doesn't really matter. So yeah, I guess let's declare all of the types, which will just look like this. I suppose. Perhaps. Is that sufficient so that we can then, you know, call them later on? Yeah, this is exactly what I envisioned. We only want to be able to declare pointers to them, so nope, not enough. Unknown type enum of empty more of empty more of int rec1. Hang on. Okay, this is the type from the error message, and it's the exact same type. So how does it say unknown type when it's like pre-declared up there? That is like, yes. Okay, so we have declarations. This is like, yeah, this, okay. Types kind of declarations and definitions. This is weird. Unknown type name. Oh wait, because there's not a type def. Type def. Oh, can we do stuff like this? Let me just try this out and then see if this works. Nope. Declare but not define type. C, declare type. Declare but not define type with type def. Like, I don't want to write struct something everywhere. Nope. Type def declaration is a definition. Okay, so I think we will just, I guess, define the structs then. Oh, and maybe then we can have type defs, like type def struct, type int. I want that struct to be known under this type. And then here we don't, oh. Okay, it doesn't work for built-in types of, okay, so, I mean, we can turn that into a struct actually. We can turn every type into a struct. These are all structs. Let's see, primitive, yeah, this is an int, but this is a struct. This is a struct. This is a struct. Struct. Yeah. Okay, so let's do that. Let's define struct something. Then once we've done that, we type def that to the same name without the struct prefix. I can't believe that's something you need to do in C. I mean, okay. Okay, yeah. And then in here we don't need type def anymore because that happened above. oh, yeah, no, instead you just define a struct with that name. And for example, for ints, this will just be the value, like this. For strings, something pretty similar actually, you know, like you have a struct, then the name, and then this. For types, just an empty struct. Sure. Then for never, you have an empty struct as well, which, I mean, I guess, yeah. Oh, wait. We can simplify that. Oh, I love that. So let's just say this is really just struct, and then type.angle, and then an opening brace, and then a new line, and we don't need this, and we don't need this, because we can inline that here, and we don't need this or this, because this just automatically happens down here. That's beautiful. Now we have the value indented, because why not? We don't need that, we just have some data and a length like this. Sure. Yeah, here we have nothing actually. Yeah, never doesn't contain anything. An enum, oh yeah. That's like contains a tag, contains a union with things, and doesn't need this. Okay, yeah, I like that, I think. Let's try that out and see how this looks. Can I reload this file or like? Okay. Yeah, so int is a struct, and this is a struct, and this is a struct, and this is a struct, and all of them are first defined up here. First declared up here, so that then we can just use pointers to them, and we don't get in trouble for that. I hope. I haven't tested this out from the command line yet. Okay, yeah. Here we have the tag, and instead of the variance being right here, let's actually like yeah, we basically want to print something a little bit more beautiful, like variant.index equals variant.item.key. So basically that we see 0 equals more, and that's it. Yeah, 0 equals more, 0 equals empty, and for types with multiple variants we see this. Okay,
yeah, we have types. We have errors because integers, of course, don't work because we've changed that to be a struct, which is expected, but still pain. So let's look for ints here and change this to be int value. And this is actually like pretty similar to what we do down here, so I'm fine with that. And then let's maybe look at the instructions, because those will be like entirely broken as well. Yeah, really, we don't want any, you know, like pointer stuff like this with a star in front of that. But instead, let's just how's it that for some cases it's at the beginning and for some not? Well, there it is. We basically want this. Yes, 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 yes. We allocate an int memory for the int value. We set that value. Beautiful. And this, okay, I thought this would work. Oh no, of course. Yeah, this also doesn't make sense. And instead we do this. Okay, okay, nice. Same here. This is just argc value. And bam. Okay, now let's actually try to compile that. Whoa. Almost working. Okay. So, oh wait, main 20 doesn't exist. Why not? Main underscore 20 underscore int. Main underscore 20 underscore int. Oh, uppercase int. For some reason, I don't know why, but sure. Weird. Well. Oh, I know why. Yeah. Because we changed types to be like, types are just a primitive type, and then we just write down the name, whatever that is. Okay. Yeah. Getting better and better. Oh. Well. Okay, so one remaining error. 174. Here. Oh, I think this is where we get into the recursive casting, I'm afraid. So more is actually hang on. The type of this is more or int or empty. And now we cast that into this.
So if it's more, then, I mean, this is correct. Yeah, because this can be both empty and more is variant 1. And then we say, okay, the first payload is an integer. Sure, that works. And the second payload, now it gets weird. Now it gets really, really weird. Yeah, the second payload is, it was this right here. Something that can only ever be empty. And we can convert that into a pointer to this. AKA to this enum. I think casts can be recursive. Yeah. If we have a list of false, we probably want to be able to cast that to a list of bool. Oh shit. So we need some, you know, like recursive thing to walk over the list recursively and allocate memory for that and so on. I mean, apart from that, let's just say this. Should be fine for now. Okay, let's also print this maybe, you know? In here, main returns an int, so let's just say printf of that integer. Okay. Now result is this. Boom. Oh, true. I mean, yeah, this is a long integer. Okay, result is 3. That's actually expected. Okay, how would we do that? We would say type int result, and then we'd say result equals this, and then we print the result value. Yeah, that's actually change that here. True. Nice. Okay, and that's expected because this returns the length of the list, and the length of the list is 3. Okay. Let's actually like maybe get the first item, and the list is 0 indexed, so this should return 2. No. Oh, well, yeah, we don't have pipes or anything like that. I'm sorry about that. Oops. Yeah, get with L and 1. there is no function named get. Oh. Oh, yeah, there is only get maybe. And that returns a maybe. So let's actually like define, I don't know, maybe. So let's define unwrap. Takes the maybe, which is a maybe t, returns a t. And it's defined as switching on the maybe. If it's some t, it just returns t. If it's none, then it calls crash. Crash is built-in crash called unwrap on none. So then we can define list.get as something that calls get maybe on the list and the index, and then calls unwrap on that result. Okay, so there are obviously some okay, you switch on this, but you don't handle the equals variant. Don't. Okay. Equals with S. Hang on. Build and compare should just less or equal or greater, not equals. Maybe that's it. Like, I don't know where that is called, but maybe, oh yeah, here we have equals index 0, which then less equal or greater. So actually there's an error in here where the ordering is actually equal or greater. And this worked. What? I mean, this is like pretty complex code, you know. Wow. Look at all these functions. Let's maybe, you know what, let's pick some more interesting values. Let's like say this is a list containing 10, 11, and 12. Like 41, 42, and 43. Okay, we compile that to C. Nope, this won't work. This will definitely not work. Wait, where's that happening? 181. So checking if two ints are equal, we call, equals with 1 and 0. Okay, so this returns something, you know, it's less or equal or greater, which seems fine to me, to be honest. Oh, but this returns type greater. Why does it do that? The type of that is... Maybe we need some more upcasting of values. Like, you know, casting in general is kind of weird right now. That is sad. Okay. suppose let's think about how we would need to cast things. Does it make sense to have casting stuff in the yogurt already? It probably does, right? Because here we basically walk the structure of those types, we do all this crazy stuff. And I mean, look at the operations. We have some param reference, we have a comp time known value of some type. We have a switch, a tag, a call, a yogurt ID, which is being cast to another type. Yeah, I'm not sure what to do about this. Yeah, no, I think the yogurt is a pretty clean stage right now. I like that we have, like, for example, all of the values, they also have types. And it's also non-trivial to convert the value to that type, because the type may be, I don't know, bool, for example, while the value is only true. So you already need to think about how do I like map these known value enum variants to these general types. That's also a kind of casting if you look at that from this lens. And casting is just something more explicit. So I don't think the cast operation is so out of place here. I think instead it would make sense to have another compiler stage then, where we probably lower these things further. Yeah, where we don't have comp time, like any comp time value anymore. Maybe. So the thing is, you don't want to put too much complexity in the transformation from one compiler stage to the next, because then the stages, that transformation becomes difficult to reason about. And I think it's already quite, like the yogurt, the transformation from egg to yogurt is the most complex transformation that we have, I think. All the interesting stuff like the type checking and so on happens here. And like most of the complexity is already in this types and the type file that we extracted. And still it's like 500 lines. So I think it makes sense to, instead of complicating this even further, create a new compiler stage with no cast in there. Yeah, no cast, no, like, maybe values, but values don't need to have types anymore. Because at this stage we don't need to look up functions or something like that. We can just completely focus on optimizing code. Yeah. Remember when we were designing the type system, and I was like, we don't want something like this is some int, but we don't know what the int is. In the next stage, maybe that makes sense, because that may allow us to optimize the code further. Right. So while this stage was all about resolving functions, and most importantly, this is the types in this stage. They are the types that the user of the code can observe. These are the types, when you call type of in your code, these are the types that you get. Next would be adding a more like granular type system, something that allows more optimizations. Where maybe we have casts explicitly in the code, and not as this, but instead as a switch, basically exactly, so that there is no difference between this C code and this C code here. That both are just a switch, because in both cases you need to handle all the cases. Yeah. Okay, so we have known types. Types are as precise as they can be. Switch is explicit. Stuff like that. Makes sense. Yeah, I'm not gonna do that today. Let's just try to compile this, and I'm pretty sure it won't work. Because right here it tries to cast a greater, where the tag is 0, to this right here, to less. Yeah, if we just assign a pointer to this, to a pointer to that, then the tag value of 0 will be interpreted as less instead of greater. So this will most definitely not work. Yeah, and here, like, this kind of worked out. That's actually why I went ahead with executing that and like working with that. But in this case, nope. Let's try this anyway. Okay, it does work. Well, yay, I guess. Sure. So yeah, the lowering to C is kind of buggy, especially casting enum values. But the rest works. Okay, so we're not gonna implement the next stage. But do I want to like program a bit more other stuff? I could, for example, look at, we have, it's crazy that we just have, linked lists now. We have linked lists and pools. Okay, I'm gonna do something like totally unrelated and just work a bit on the standard library, maybe let's call it. Not really a standard library, because we don't have a separate file for that, but and in order to do that, I'm actually gonna add syntax highlighting for this language. And that's kind of pain, to be honest, because I forget all the time how that works. In VSCode there is like, you need to create an extension and stuff like that. So what I am gonna do is just copy that stuff from Martinez. So that's like the main language that I'm working on. And you can see that there's a VSCode extension folder. And yeah, let's do something like that for breakfast as well. Yeah, so okay, I'm just gonna copy the folder. So here we have Martinez. And here we have breakfast. And let's just copy the VSCode folder, I guess. VSCode extension, copy that. Moved, no. Copied, okay, I guess. Okay, so VSCode extension, what does it contain? And maybe also, how did I create this? If you look for VSCode, create VSCode extension, you will have this nice guide, your first VSCode extension. And you know, you can run all these weird fancy commands. For me that didn't work actually. Like I tried to do this yo code and it just asked me some stuff and then there was an error and I was like, okay, well, that kind of sucks. And then I copied the folder from another project. But also it uses TypeScript, which is fine, I mean, you know. But it also adds a lot of like complexity, because then you need to have the TypeScript pipeline running and stuff like that. And I mean, yeah, it kind of works, but I mean, okay, let's just go through these. And here we have a CPU profile, which I guess let's not do that. Here we have compiler options, which sure, I'm not sure why we need that, but okay. So the name of our language is breakfast, displayed as breakfast, like this. Breakfast language support, publisher Marcel, repository is this. Okay, yeah, this is like programming versions. Yeah, we don't have like custom colors defined. So this doesn't contribute colors, it doesn't contribute commands, it does contribute a grammar, which is the breakfast grammar, which is right here in breakfast. .tm grammar.json, and this is like a text-made grammar, I think. Okay, language is breakfast extension. I mean, okay, yeah, no, it's brainfuck, but let's just go with df. Okay, yeah, I guess that's sure. And then we have this log file, which I think you need to do like npm something, npm install, and this updates the log file. And of course there are vulnerabilities because that's the JavaScript ecosystem. Yeah, we don't have comments right now, but maybe we'll use a hashtag for that. We don't have, oh yeah, we do have round brackets, but not these. And so the round brackets are also the auto closing ones. And if you type this, like if you type this, you can see that automatically it inserts another one. And if you type this, it also automatically inserts a closing parenthesis. Yeah, we only want that for these because the other things don't need anything. Like braces or these kind of brackets, they don't mean anything in breakfast. Okay, so if in the line before there was something, I think that's what it means, and then spaces, I don't know, the beginning of the line followed by some white space, followed by a pipe character and then something, and then the line ends. So basically if the line before is only consists of a comment, then we also want to you know, start this line with a comment. Yeah, sure. Nope. And I guess nope. I mean, like, to be honest, we don't really need to do anything right now. We can, if we want to do something, we can still to like ignore this warning. Yeah, okay. Yeah, I'm not sure if you can, there's probably a way to just disable this extension thing altogether, but okay, run extension is a thing. Run breakfast extension, so that things are not confusing. And the grammar of the extension is interesting. So we won't have any comments. We don't really have keywords, to be honest. Neither control flow nor like other keywords. Yeah. No, not really. I mean, keyword operator. Equals is an operator, and percent. These are like special keyword things. Everything else, not really. Okay, yeah, there is not an asm thing. Like, this is for in Martinez, you can do an asm syntax highlight. So if you have an asm function, then down here is assembly. You can do this, and you get syntax highlighting for that. Like this. But so you basically have multiple modes that you can switch between, which is also this and what this repository is about. The repository defines some like top level kind of context that you can be in. We saw a comment context where you can basically do everything. We had an all context, which is like the usual expression thing. And here we have this asm context where, you know, the different soil registers, they are highlighted differently than the instructions, and they're highlighted differently than labels, for example. But really, we don't have that. We just have one thing. So we can also just maybe copy that up here. I'm not sure. Yeah, but we don't have some asm thing. We don't support comments in here. We do support strings. Yeah, begins with quotes, ends with quotes. We don't have string interpolation yet. So, you know, this is basically where you have this string thing, and then inside of that, you basically try to match the expressions again and highlight them differently. Inside of string interpolation, we have the normal highlighting. Yeah, here we don't really have that. And I'm not sure if we even have like character escaping. I don't know. Okay, but then there are numeric constants, which, I mean, I guess, sure. And we don't have any hexadecimal stuff or stuff like this. So this is just 0 to 9, possibly multiple of that. Yeah, we don't have, I don't even know what that is. Characters, nope, no character literals. Functions, yeah, we do have functions. Or variables, really. Yeah, variable. There was no, like in Martinez, it's pretty easy to distinguish a function because it has a name, and then this is basically like a look ahead pattern. It doesn't consume what is defined here, but this has to match for the entire rec expression to match. So after the name, there has to come possibly some white space and then an opening, opening parenthesis, or I don't even know, an opening like bracket if you have a function with type parameters that you explicitly give to that, and stuff like that. But we don't have that. We just have this case for variables, which are lowercase, and types are uppercase. I mean, in reality, also like uppercase symbols and stuff like that. But for now, that will just be highlighted the same way as types. Right, this is not an asm function. And yeah, let's just see what we have here. Oh, I see. I think I need to open. You know what? I think it makes sense to have two instances of VSCode open. One, this instance right here, and then another instance. Why is it fuzz? What? Where's that error coming from? From here? No errors here. Fuzz and string, but that's like that's only because the string file is open. But apart from that, I'm not sure why, why does it want that? Found not found. The file is in the program because match by default. But why is it? Okay, so I just saved it and now it's gone. Yeah, this is JavaScript. The build tooling is kind of meh. Okay, new VSCode instance, and in here I'm going to open a folder, namely the breakfast VSCode extension folder, and it just crashed, I think. Yeah, all of VSCode just crashed. That's certainly interesting. Let's try to open just that folder, maybe. Yeah, open recent. Nope. Okay. Open breakfast VSCode extension, and it crashed again. How? I mean, how can an editor be so broken? Honestly, I don't get it. I really don't get it. Is there something in here that makes it hate itself so much that it just quits? I don't get it. Okay, activation events should probably, if something in the workspace has the .pf file extension. .mar, no. Okay. Okay, sure, but that doesn't, that won't cause VSCode to crash. Wait, what? Maybe I'm due for upgrading. Oh, but VSCode was on FlatHub, I think. Yeah, I don't know. Okay, let me actually VSCode, current VSCode version, because my version is
about VSCode 1.94 from 3 days ago. Yeah. So it is up to date. And like this is not, like this happens for all VS Code instances. You know, I have another VS Code instance here in the background. And here just open the breakfast folder. And all of VS Code just crashes. Yeah, I guess with that I'm I'm just gonna leave it like that. Hopefully I'm going to get this fixed until the next coding session somehow. Yeah, until then we achieved quite a bit today. We have clean types. Sure, the lowering to C is not perfect. It allocates memory all over the place, and casting types doesn't work right now. But apart from that, you can actually, like, we have implemented linked lists and they kind of work. That's crazy. We have pattern matching, and you can actually like traverse down into recursive types, like this list len function here, or get function. Like this is nice. It's really nice that this just works. And I feel pretty comfortable with that. Like the type solving code it's not easy maybe to write, but there are descriptive comments above all of the operations, and you know, if you read through them, they are logical. Like everything in that makes sense. So yeah, I guess next up would be probably another compiler stage that is more precise with types, that allows things such as casting to be optimized into, you know, like basically instead of just having a cast expression that just magically does things, we have like recursive calls and switches and so on. And also just it would be nice to be able to just optimize code like extremely well. So that's probably what we're going to look into next. Not the optimization part, but designing a compiler stage and compiling to that, and you know, generating nice C code from that and going from there. That's the one route that needs work, you know. And the other route would be to actually look at some language tooling, look at syntax highlighting, which is kind of like VS Code is broken right now, but yeah, basically you have syntax highlighting, maybe you have a language server. If there's an error in a file, we don't just want to print this is the error, we also want to print like which line is it from, and we basically need to be able to track errors back into the original source code. So there are a lot of like usability things that still need figuring out. But the main, like the hard part, I think, is over. The actually like difficult part of how do we deal with recursive types? How do we traverse down into them? How do we make function overloading? That's what makes this language unique among all languages. This combination of these structural typing and overloading and all these features, that's basically done. Yeah, sure, there are some comp time features we can still add, but yeah, it's making progress, good progress. So I guess see you next time, and have a nice week. Bye.